In the darkness between stars, 124 light-years from Earth, orbits a world that has rewritten the rules of what we thought possible. K218b, a planet so tantalizingly close to harboring life that scientists have assigned it a 99.7% habitability score. But here's what most people believe, that finding life requires an Earth-like world, orbiting a sun-like star, with familiar conditions we recognize from home. And yet, K218b challenges every assumption we've ever made. It's a sub-Neptune, larger than Earth but smaller than Neptune, wrapped in a hydrogen-rich atmosphere that should be hostile to life as we know it. It orbits a red dwarf star, a type of sun that flares with deadly radiation and burns for trillions of years. So how did this alien world earn the highest habitability rating of any planet we've ever discovered? And what secrets does its star system hold that could reshape our understanding of life in the universe? Join me as we journey to one of the most fascinating planetary systems ever discovered, where the impossible seems not just possible, but probable. Before we embark on this cosmic journey together, I'd love to know, where in the world are you watching from right now? And what time of day is it? Drop your location and local time in the comments below. It's amazing to think that no matter when or where you're watching this, K218b continues its silent orbit, potentially harboring the greatest discovery in human history. October 2023. Deep in a laboratory at Cambridge University, astronomer Niku Madhusudan stares at data that shouldn't exist. The James Webb Space Telescope has just delivered spectroscopic readings from a world called K218b, and the numbers dancing across his computer screen represent something unprecedented in the history of astronomy. The story begins much earlier, in 2015, when NASA's Kepler Space Telescope first spotted K218b through the transit method, that ingenious technique where we detect planets by watching them pass in front of their host stars, causing a tiny but measurable dip in starlight. The story begins much earlier. Think of it like watching a moth flutter past a street lamp from miles away. The shadow is almost imperceptible, but it's there. But K218b's transit signal was special. The planet took 33 Earth days to complete one orbit around its red dwarf star, placing it squarely in what astronomers call the habitable zone, the Goldilocks region, where temperatures are just right for liquid water to exist. This alone was exciting, but not revolutionary. We'd found habitable zone planets before. What made K218b extraordinary was its size. At 2.6 times Earth's radius and roughly 8.6 times its mass, it belonged to a category of planets that simply doesn't exist in our solar system, sub-Neptunes. These worlds are larger than the biggest rocky planets, but smaller than ice giants, representing the most common type of planet in our galaxy. And yet, we had no idea what they were actually like. The early data suggested something remarkable. K218b might have water vapor in its atmosphere, but water vapor alone doesn't make headlines. Planets throughout the galaxy show traces of water. What needed to be determined was whether this water vapor was part of a thick, steamy atmosphere surrounding a hellish world, or something far more intriguing. Fast forward to those October nights in 2023, the James Webb Space Telescope, with its unprecedented infrared vision, had spent precious observing time studying K218b's atmosphere as starlight filtered through it during transits. What Madhusudan and his team found defied expectations. The spectroscopic signature showed not just water vapor, but carbon dioxide and tantalizing hints of dimethyl sulfide, a molecule that on Earth is only produced by living organisms. But even more shocking was what they didn't find: the expected signatures of a thick hydrogen atmosphere that should have made this world uninhabitable. Instead, the data suggested something that seemed impossible. K218b might be what astronomers now call a Haitian world, a hydrogen-rich planet with a global ocean beneath its atmosphere. Picture, if you will, a world where an entire planet is covered by a deep, dark ocean, protected by a thick but not crushing hydrogen atmosphere. It's unlike anything we've imagined, let alone discovered. The implications hit the scientific community like a shockwave, within hours of the paper's release. K218b became the most talked about planet beyond our solar system. Social media exploded with speculation. News outlets struggled to convey the significance. And somewhere in the endless stream of data, a habitability algorithm assigned K218b a score that would make it famous, 99.7%. But what does that number actually mean? And how did we arrive at it? That's where our story truly begins. Numbers in astronomy can be deceptive. When we say K218b has a 99.7% habitability score, we're not claiming there's a 99.7% chance that life exists there. Instead, this percentage represents how closely K218b matches the conditions we believe are necessary for life as we understand it. The habitability index takes into account multiple factors: stellar radiation levels, atmospheric pressure, temperature ranges, the presence of liquid water, and atmospheric composition. It's a complex calculation that weighs each variable against what we know supports life on Earth. Think of it as a cosmic report card, where Earth would score 100%. What makes K218b's score so remarkable is that it achieves this rating while being fundamentally different from Earth. Our planet scores highly because we know life exists here. It's our reference point. But K218b scores nearly as high, while being a completely different type of world in an alien star system. The water vapor detection was crucial to this score. Hall spectroscopic analysis revealed that K218b's atmosphere contains significant amounts of water vapor, or not just trace amounts, but enough to suggest that water plays a major role in the planet's atmospheric chemistry. On Earth, water vapor in the atmosphere comes primarily from evaporation of our oceans. The presence of substantial water vapor in K218b's atmosphere hints at a similar process occurring on a global scale. But the 99.7% score also reflects what scientists call the Goldilocks principle. Taken to its logical extreme, K218b sits in the habitable zone of its star, where temperatures allow liquid water to exist. However, unlike rocky planets such as Earth or Mars, K218b's larger size and different composition create a unique environment where habitability might work in ways we've never considered. The carbon dioxide detection adds another layer to the habitability score. CO2 in an atmosphere can indicate geological activity, weather patterns, and complex atmospheric chemistry, all processes that could support or regulate conditions favorable to life. More intriguingly, the ratio of water vapor to carbon dioxide in K218b's atmosphere suggests a world where these gases interact in ways that could maintain stable, temperate conditions over long periods. Perhaps most tantalizing is what the 99.7% score represents about our expanding understanding of habitability itself. For decades, we've searched for Earth 2.0, a rocky planet orbiting a sun-like star at just the right distance. K218b forces us to reconsider this approach. Here's a world that might be habitable precisely because it's nothing like Earth. The habitability index that generated this score considers the possibility of life in environments we're only beginning to understand. Sub-Neptunes like K218b might represent a new category of habitable world, one where life could thrive in global oceans beneath hydrogen-rich atmospheres, protected from harmful radiation, while maintaining the chemical complexity necessary for biology. But to understand how K218b earned this unprecedented score, we need to examine the star that makes it all possible. Because, without its host star, a red dwarf designated K218, none of this would be possible. K218 doesn't look like much. If you could somehow transport yourself to this star system and observe it with your own eyes, you'd see a dim, orange-red star roughly half the mass of our Sun, glowing with about 2.3% of the Sun's luminosity. It's the kind of star that ancient astronomers would have dismissed as unremarkable if they could have seen it at all from Earth without a telescope. But K218 represents something profound about our universe, the power of the small and patient to nurture the extraordinary. Red dwarf stars, also known as M-dwarf stars, are the universe's great survivors. While massive, brilliant stars burn bright and die young, sometimes lasting only millions of years, red dwarfs are the marathon runners of stellar evolution. K218 is approximately 2.3 billion years old. Still in its stellar infancy, it will continue burning hydrogen in its core for another trillion years, long after our sun has expanded into a red giant and died. This longevity is crucial for understanding K218b's habitability. Life, as we know it, requires time, enormous amounts of time, to evolve from simple chemical processes to complex organisms. On Earth, it took nearly 4 billion years for life to evolve from single-celled organisms to the complex biosphere we see today. K218's incredible lifespan means that any life that did emerge on K218b would have virtually unlimited time to evolve and develop. But red dwarfs present a paradox for habitability. Their habitable zones, the regions where liquid water can exist, are much closer to the star than Earth is to the Sun. K218b orbits its star at a distance of about 0.14 astronomical units, roughly 1/7 the distance between Earth and the Sun. At this proximity, you might expect the planet to be tidally locked, with one side permanently facing the star and the other in eternal darkness, creating extreme temperature gradients that would make habitability unlikely. However, recent models suggest that K218b might not be tidally locked, or if it is, its thick atmosphere could redistribute heat efficiently enough to prevent the extreme temperature differences that would make the planet uninhabitable. The star's relatively stable energy output, combined with the planet's substantial atmosphere, creates conditions where global circulation patterns could maintain temperate conditions across much of the planet's surface. 4. K218 also presents unique advantages for detecting and studying planets. Because red dwarfs are smaller and dimmer than sun-like stars, planets orbiting in their habitable zones cause more pronounced dips in starlight during transits. This makes it easier to detect these worlds and study their atmospheres. The contrast between planet and star is more favorable, allowing telescopes like JWST to gather detailed spectroscopic data that would be nearly impossible to obtain for similar planets orbiting brighter stars. The star's spectral characteristics play a crucial role in planetary atmospheres. Red dwarfs emit most of their energy in the near-infrared spectrum, which has profound implications for atmospheric chemistry and the potential for photosynthesis. Any life that evolved on K218b would need to adapt to this different quality of starlight, potentially developing entirely new biochemical pathways for harvesting energy. One of the most significant concerns about red dwarf habitability involves stellar flares. Young red dwarfs, in particular, can produce powerful flares that blast their planets with harmful X-ray and ultraviolet radiation. These flares can strip away planetary atmospheres over time, leaving worlds barren and exposed. However, K218 appears to be a relatively quiet red dwarf. While it does produce flares, they're not as frequent or intense as those seen in younger, more active red dwarf systems. The star's metallicity, the abundance of elements heavier than hydrogen and helium, is also crucial for understanding the K218 system. Spectroscopic analysis reveals that K218 has a metallicity similar to our Sun, meaning it contains sufficient heavy elements to form rocky planetary cores and complex atmospheric chemistry. This metallicity suggests that the star formed from material enriched by previous generations of stars, providing the building blocks necessary for complex planetary systems. Perhaps most intriguingly, K218's position in our galaxy places it in a region with relatively low stellar density and minimal gravitational disruption from neighboring stars. This cosmic quiet zone has allowed the K218 system to evolve undisturbed for billions of years, providing the stable environment necessary for complex planetary evolution. The star's mass and evolutionary state also mean that its habitable zone will remain stable for extraordinary periods. Unlike more massive stars, which evolve quickly and render their planets uninhabitable as they age, T218 will maintain consistent energy output for timescales that dwarf the entire history of complex life on Earth. Understanding K218 is essential because stars are the architects of their planetary systems. They determine not just where planets can maintain liquid water, but also the types of atmospheric chemistry possible, the radiation environment planets experience, and the timescales available for biological evolution. K218, despite its unremarkable appearance, has created the conditions that allow K218b to earn its remarkable 99.7% habitability score. But KAV-218b doesn't exist in isolation. As we're about to discover, it's part of a complex planetary system with its own intricate gravitational ballet, a cosmic architecture that may hold additional secrets about habitability and life beyond Earth. Imagine trying to map a city at night from an airplane, but you can only see the streetlights when cars drive past them. This is essentially how astronomers have pieced together the architecture of the K218 system, using brief moments when planets cross in front of their star to reveal the hidden structure of an entire alien solar system. The K218 system is far more complex than early observations suggested. What began as the discovery of a single intriguing planet has evolved into the recognition of a multi-planet system with its own unique dynamics and gravitational relationships. Each new observation has added pieces to a cosmic puzzle that challenges our understanding of how planetary systems form and evolve. K218b, our 99.7% habitability star, is not alone. Gravitational analysis and careful observation have revealed the presence of at least one other planet in the system, K218c. This second world orbits closer to the star than K218b, completing its orbit in just 9 Earth days. So, K218c is smaller than its more famous sibling, roughly 1.9 times Earth's radius, and likely represents a different type of world entirely, possibly a rocky super-Earth or a smaller sub-Neptune. The relationship between these two confirmed planets tells a fascinating story of system architecture. They exist in what astronomers call a resonant chain, where their orbital periods are related by simple mathematical ratios. For every 3 orbits K218c completes around the star, K218b completes approximately 1. This 3 resonance isn't coincidental. It's a fingerprint of how these worlds formed and migrated to their current positions over millions of years. But the story doesn't end with 2 planets. Subtle variations in the timing of K218b's transits, tiny deviations from the clockwork precision we'd expect if it were orbiting alone, suggest the gravitational influence of additional unseen worlds. These transit timing variations, or TTVs, are like cosmic breadcrumbs that reveal the presence of planets we cannot directly observe. Current models suggest the possibility of a third planet, tentatively designated K218d, orbiting farther from the star than K218b. This outer world would have an orbital period of perhaps 60 to 90 Earth days, placing it at the outer edge of the star's habitable zone, or possibly beyond it. If it exists, K218d might represent yet another type of world, perhaps a cold super-Earth or an ice-rich planet that could harbor subsurface oceans beneath a frozen surface. The mass distribution within the K218 system reveals something remarkable about planetary formation around red dwarf stars. The total mass of the known planets is substantial collectively. They contain roughly 15 times the mass of Earth. This represents a significant fraction of the solid material that was available in the original protoplanetary disk from which the system formed. What makes this architecture particularly intriguing is how different it is from our own solar system. In our cosmic neighborhood, the inner planets are small and rocky, while the outer planets are gas and ice giants. The K218 system appears to be populated entirely by intermediate mass worlds, sub-Neptunes and super-Earths that represent planet types absent from our solar system. This architectural difference has profound implications for understanding planetary formation. The K218 system appears to have formed through a process where solid materials accumulated efficiently into intermediate mass cores. which then accreted substantial but not overwhelming atmospheres from the surrounding gas disk. The result is a system of worlds that exist in the middle ground between rocky planets and gas giants. Umozkal, the systemateri Siniefa Novingintis, and Akaunda Novinginsivingar, Uriefa Novingintis. The spacing of planets in the K218 system also tells us about the migration history of these worlds. The current orbital configuration is the result of a complex dance that unfolded over millions of years as gravitational interactions with the protoplanetary disk and between the planets themselves shaped the final architecture we observe today. Recent computational models suggest that the K218 system may have originally formed with planets in different positions, and that gravitational interactions caused them to migrate inward over time. Weibel-Pime, this migration process is crucial for understanding how K218b ended up in the perfect position within the habitable zone. It may not have formed there, but rather drifted into this Goldilocks location through the gravitational choreography of system evolution. The implications extend beyond just understanding how these particular worlds formed. The K218 system serves as a laboratory for studying the most common type of planetary system in our galaxy. Red dwarf stars host the majority of planets we've discovered, and many of these systems show similar architectures to K218. Multiple intermediate mass worlds in compact orbital configurations. Understanding this architecture is crucial for assessing habitability, not just on K218b, but throughout the system. The gravitational interactions between planets affect their climates, their atmospheric evolution, and even their potential for maintaining stable conditions over geological time. As we'll discover, the position of K218b in this cosmic architecture is no accident. It's precisely what makes its remarkable habitability possible. The concept of a habitable zone seems simple enough. It's the region around a star where temperatures are just right for liquid water to exist on a planet's surface.
Too close.
And water boils away into space. Too far, and it freezes solid. But K218b presents us with a paradox that's forcing astronomers to completely rethink what habitable actually means. Traditional habitable zone calculations assume rocky, terrestrial planets with thin atmospheres, worlds like Earth, Mars, or Venus. But K218b is neither rocky nor does it have a thin atmosphere. It's a sub-Neptune with a substantial hydrogen envelope, orbiting in a habitable zone designed for completely different types of worlds. By conventional wisdom, it shouldn't be habitable at all. The paradox deepens when we consider the atmospheric pressure on K218b. Early models suggested that sub-Neptunes like this world would have crushing hydrogen atmospheres, perhaps hundreds of times thicker than Earth's atmosphere. Under such conditions, the surface pressure would be so intense that water couldn't exist as a liquid. Regardless of temperature, it would either be forced into exotic high-pressure ice phases or remain as supercritical fluid that's neither liquid nor gas. But the James Webb Space Telescope observations revealed something unexpected. The spectroscopic signature of K218b's atmosphere doesn't match what we'd expect from a world with an overwhelmingly thick hydrogen envelope. Instead, the data suggests a more moderate atmosphere, substantial enough to retain heat and protect the surface, but not so thick as to create uninhabitable pressure conditions. This observation led to the development of the Haitian world hypothesis, the idea that K218b might be covered by a global ocean beneath a hydrogen-rich atmosphere, with pressures only 10 times that of Earth's atmosphere. In this scenario, the hydrogen envelope acts like a cosmic greenhouse, trapping heat and maintaining liquid water at the surface, despite the planet's distance from its dim red dwarf star. The temperature dynamics of this proposed Haitian world are fascinating. Climate models suggest that K218b's surface temperatures might range from 0 to 50 degrees Celsius, well within the range where life as we know it could potentially exist. The hydrogen atmosphere would distribute heat efficiently around the planet, preventing the extreme temperature variations that might otherwise occur on a world so close to its star. But here's where the paradox becomes even more intriguing. K218b might actually be more habitable than Earth-like worlds in the same star system would be. A rocky planet at K2-18b's distance from the red dwarf K2-18 might be tidally locked, with one side perpetually scorched and the other frozen solid. The substantial atmosphere of K2-18b could prevent tidal locking, or at least moderate its effects, creating more stable global conditions. The habitable zone around K2-18 is also different from the habitable zone around our Sun. Red dwarf stars emit most of their energy in the near-infrared spectrum, which penetrates deeper into planetary atmospheres than visible light. This means that the effective habitable zone around K2-18 might be broader than traditional calculations suggest, particularly for worlds with substantial atmospheres that can trap and redistribute this infrared energy. Recent research has even suggested that the habitable zone around red dwarfs might extend much farther than previously thought. When we consider planets with hydrogen-rich atmospheres, these worlds could maintain liquid water at distances where rocky planets would be frozen solid, effectively expanding the habitable real estate around the most common stars in our galaxy. The K2-18b paradox is reshaping our entire approach to astrobiology. Instead of looking exclusively for Earth analogues, we're beginning to recognize that habitability might be more common and more diverse than we ever imagined. Worlds like K2-18b, if they're truly habitable, would represent a new category of life-bearing planet, one that could be far more numerous than Earth-like worlds. This paradigm shift has profound implications for our understanding of life in the universe. If sub-Neptunes in the habitable zones of red dwarf stars can support life, then the number of potentially habitable worlds in our galaxy increases dramatically. We're not just looking at a few Earth twins, we're looking at an entire cosmos of alien oceans beneath alien skies. This paradigm shift has profound implications for our understanding of life in the universe. If sub-Neptunes in the habitable zones of red dwarf stars can support life, then the number of potentially habitable worlds in our galaxy increases dramatically. But to understand how remarkable K2-18b truly is, we need to meet its companions in this cosmic dance. In the gravitational ballet of the K2-18 system, K2-18b may be the star performer, but it's not dancing alone. The subtle gravitational tugs and pulls recorded by our most sensitive instruments reveal a system populated by multiple worlds, each playing a crucial role in maintaining the delicate conditions that make K2-18b's remarkable habitability possible. K2-18c, the inner planet, completes its scorching orbit in just 9 Earth days, racing around its red dwarf star at a distance of only 0.07 astronomical units, closer than Mercury is to our Sun. This world experiences temperatures that would melt lead, with a radius roughly twice that of Earth. K2-18c likely represents what astronomers call a super-Earth, or possibly a smaller sub-Neptune that has been stripped of its atmosphere by stellar radiation. The relationship between K2-18c and K2-18b is far from coincidental. These worlds are locked in a 3-orbital resonance, a gravitational relationship that keeps them in perfect synchronization across cosmic time. This resonance is like a cosmic metronome. For every 3 orbits K2-18c completes, K2-18b completes exactly 1. Such precise relationships don't occur by chance. They're the result of a complex migration process that unfolded over millions of years as these worlds formed and settled into their current positions. This resonant relationship serves as a cosmic stabilizer for the entire system. The gravitational interaction between the 2 planets helps maintain stable, nearly circular orbits that prevent dramatic climate variations that could destabilize conditions on K2-18b. Indefined is, without K2-18c's gravitational influence, K2-18b's orbit might be more eccentric, causing it to swing closer to and farther from its star in ways that could disrupt the delicate temperature balance necessary for its potential habitability. But the system's architecture extends beyond these 2 confirmed worlds. Transit timing, variations, minute changes in when K2-18b passes in front of its star, suggest the gravitational influence of at least one additional planet. These variations are incredibly subtle, measured in seconds or minutes over years of observation, but they provide compelling evidence for unseen companions in the outer reaches of the system. The most likely candidate for this third world, tentatively designated K218d, would orbit at roughly twice K218b's distance from the star, with an orbital period of approximately 60 mighty Earth days. This places the hypothetical planet at the outer edge of the habitable zone, or possibly in what astronomers call the extended habitable zone, regions where greenhouse effects or subsurface heating could potentially maintain liquid water. If K218d exists, it would likely be a cold world, receiving perhaps 1/10 the stellar energy that K218b receives. Surface temperatures might hover around -50 degrees Celsius, too cold for liquid water at the surface. However, if K218d has a substantial atmosphere with greenhouse gases, or if it harbors internal heat from radioactive decay or tidal heating, it could potentially maintain subsurface oceans beneath an icy shell, similar to how Jupiter's moon Europa harbors an ocean beneath its frozen surface. The mass distribution within the K218 system tells a remarkable story about planetary formation efficiency. The combined mass of the known and suspected planets represents a significant fraction of the solid material that was available when the system formed. This suggests that planetary formation around K218 was remarkably efficient, with most of the available building blocks being incorporated into planets rather than being ejected from the system or accreted by the star. Recent dynamical models of the K218 system suggest it may have formed through a process called disk migration, where planets formed farther from the star and gradually migrated inward through gravitational interactions with the protoplanetary disk. This migration process could explain how K218b ended up in the perfect position within the habitable zone. It may not have formed there, but rather drifted into this Goldilocks location through the cosmic choreography of planetary migration. The orbital architecture also provides clues about the system's age and stability. The fact that these planets have maintained their resonant relationships for billions of years suggests that the K218 system has been dynamically stable for most of its history. This long-term stability is crucial for habitability, as it ensures that K218b has remained within the habitable zone for the extended periods necessary for life to potentially emerge and evolve. Perhaps most intriguingly, the K218 system's architecture might actually enhance the habitability of its worlds rather than compromise it. The gravitational interactions between planets can drive tidal heating, generate magnetic fields through dynamo processes, and maintain atmospheric chemistry through processes we're only beginning to understand. The presence of multiple worlds in the system creates a complex web of interactions that could contribute to maintaining the conditions that make K218b so remarkable. The companions of K218b remind us that habitability is not just about individual planets, but about entire planetary systems working together as complex, interconnected environments. The 99.7% habitability score that made K218b famous is not just a product of the planet itself, but of its entire cosmic neighborhood, a neighborhood we're now ready to explore in unprecedented detail through the lens of its alien atmosphere. On a clear night in July 2023, the James Webb Space Telescope turned its golden hexagonal mirror toward a patch of sky in the constellation Leo, 124 light-years away. A world twice the size of Earth was beginning its transit across the face of its red dwarf star. For the next few hours, starlight would filter through the alien atmosphere of K218b, carrying with it the chemical fingerprints that would revolutionize our understanding of habitability beyond Earth. The detection of water vapor in exoplanet atmospheres isn't new. Astronomers have found traces of water in the atmospheres of hot gas giants for over a decade. But what the James Webb Space Telescope discovered in K218b's atmosphere was unprecedented in both quantity and implication. This wasn't just water vapor, it was water vapor in abundance in a potentially habitable world, detected with a precision that allowed scientists to begin understanding not just its presence, but its role in an alien climate system. The process of atmospheric detection through transit spectroscopy is elegantly simple in concept, breathtakingly complex in execution. As Cal 218b passes between its star and Earth, starlight filters through the planet's atmosphere before reaching our telescopes. Different molecules in the atmosphere absorb specific wavelengths of light, creating a unique spectroscopic signature, a chemical barcode that reveals the atmospheric composition across vast interstellar distances. Water vapor produces distinctive absorption features in the infrared spectrum, particularly around wavelengths of 1.4 and 1.9 micrometers. The James Webb Space Telescope's unprecedented infrared sensitivity allowed it to detect these signatures with remarkable precision, revealing not just the presence of water vapor, but its abundance relative to other atmospheric components. What made the K218b detection extraordinary was the strength of the water vapor signal. The spectroscopic features were robust and unmistakable, suggesting that water vapor makes up a significant fraction of the planet's atmospheric composition. This abundance implies several remarkable possibilities about the nature of this alien world. First, the presence of substantial water vapor suggests an active water cycle. On Earth, atmospheric water vapor comes primarily from evaporation of surface water, oceans, lakes, and rivers that continuously exchange water with the atmosphere through evaporation and precipitation. The strong water vapor signal from K218b suggests a similar process might be occurring on a global scale, implying the presence of liquid water reservoirs that could span continents or even cover the entire planet. The temperature and pressure conditions inferred from the water vapor detection support the Haitian world hypothesis. The idea that K218b might be an ocean planet with a hydrogen-rich atmosphere. In this scenario, the planet's surface would be covered by a global ocean, possibly hundreds of kilometers deep, with water continuously evaporating into the atmosphere and returning as precipitation in a planet-wide weather system, unlike anything in our solar system. But the water vapor detection also raised profound questions about atmospheric dynamics on sub-Neptune worlds. Traditional models suggested that planets like K218b would have such thick hydrogen atmospheres, water would be trapped in high-pressure phases at the bottom of an atmospheric column, extending thousands of kilometers above the surface. The robust water vapor signal suggests a different scenario, an atmosphere where water can exist as vapor and participate in complex chemical and physical processes. The spectroscopic analysis revealed additional details about the water's behavior in K218b's atmosphere. The shape and depth of the absorption features provide information about temperature and pressure profiles at different atmospheric levels. The data suggests that water vapor is distributed throughout much of the atmosphere, not concentrated in a thin layer near the surface as it would be on a world with a crushing atmospheric envelope. This distribution pattern supports models where K218b has a substantial but not overwhelming atmosphere, perhaps 2 times the pressure of Earth's atmosphere, thick enough to maintain liquid water and distribute heat efficiently, but not so thick as to create uninhabitable conditions. It's a Goldilocks atmosphere, not too thick, not too thin, but just right for potentially supporting life. The water vapor detection also provides insights into the planet's formation and evolutionary history. The presence of abundant water suggests that K218b formed in a region of its protoplanetary disk where water ice was available, likely beyond the snow line, where temperatures were cold enough for water to freeze. The planet may have then migrated inward to its current position in the habitable zone, bringing its water-rich composition with it. Perhaps most significantly, the water vapor detection demonstrates the incredible potential of next-generation space telescopes to study potentially habitable worlds. The precision achieved in analyzing K218b's atmosphere represents a quantum leap in our ability to characterize Earth-sized and super-Earth-sized planets around nearby stars. What took decades of speculation and theoretical modeling has been replaced by direct chemical analysis of an alien atmosphere. The implications extend far beyond a single planet. If Key 218b truly harbors abundant liquid water beneath a hydrogen-rich atmosphere, it represents a new category of potentially habitable world, one that could be far more common in the universe than Earth-like planets. If universes de Fioli and do ITA red dwarf stars host the majority of planets we've discovered, and many of these systems contain sub-Neptune worlds in their habitable zones. The water vapor revolution sparked by Key 218b suggests that the universe might be teeming with ocean worlds of a type we never imagined. But water vapor alone doesn't tell the complete story of Key 218b's atmosphere. The James Webb Space Telescope's observations revealed a complex atmospheric composition that challenges our understanding of chemistry, climate, and habitability on alien worlds. The detection of carbon dioxide alongside water vapor opens new chapters in our understanding of atmospheric processes on potentially habitable sub-Neptunes. The water vapor revolution represents more than a scientific discovery. It represents a fundamental shift in how we think about life in the universe. For the first time, we have direct chemical evidence of abundant water in the atmosphere of a potentially habitable world beyond our solar system. This detection has transformed K218b from an interesting theoretical possibility into a compelling target for the search for life beyond Earth. The atmosphere of K218b presents one of the most intriguing puzzles in modern astronomy. How can a world dominated by hydrogen and helium, gases that should create uninhabitable conditions, instead create an environment potentially suitable for life? The answer lies in understanding the delicate balance that transforms what should be a hostile gas envelope into a cosmic greenhouse, perfectly tuned for habitability. Traditional models of sub-Neptune atmospheres painted a grim picture for habitability. These models suggested that planets like K218b would be shrouded in massive hydrogen-helium envelopes, extending thousands of kilometers above their surfaces, creating crushing pressures and temperatures that would make liquid water impossible. The surface pressure on such worlds was predicted to be hundreds or even thousands of times greater than Earth's atmospheric pressure, conditions where water would exist only as exotic high-pressure ices or supercritical fluids. But the James Webb Space Telescope's spectroscopic analysis of K218b revealed a more nuanced story. While hydrogen and helium do dominate the planet's atmospheric composition, they exist in proportions and at pressures that create surprisingly temperate conditions rather than the hellish environment theoretical models predicted. The key insight comes from understanding how hydrogen behaves as an atmospheric component on worlds in the habitable zone. Hydrogen is an incredibly efficient greenhouse gas when present in substantial quantities. Unlike carbon dioxide, which absorbs specific wavelengths of infrared radiation, hydrogen can absorb and re-emit energy across a broad spectrum of wavelengths, creating a greenhouse effect that can maintain warm temperatures even at significant distances from a star. In K218b's case, the hydrogen-dominated atmosphere acts like a cosmic blanket, trapping heat from the red dwarf star K218 and redistributing it around the planet. Climate models suggest that this hydrogen greenhouse effect allows K218b to maintain surface temperatures between 0 and 50 degrees Celsius, well within the range where liquid water can exist, despite receiving only about 1/3 the stellar energy that Earth receives from the Sun. The helium component of the atmosphere plays a supporting but crucial role. Helium doesn't contribute significantly to greenhouse heating, but it affects the overall atmospheric structure and density. The presence of helium helps create an atmospheric composition that maintains the right balance between heat retention and heat loss, preventing the runaway greenhouse effects that could make the planet uninhabitably hot. Perhaps most remarkably, the hydrogen-helium envelope appears to be self-regulating. As the atmosphere absorbs energy from the star, it expands and cools, reducing its greenhouse efficiency. As it cools, it contracts, increasing its greenhouse effect. This creates a natural thermostat that could maintain stable temperatures over geological timescales, exactly the kind of long-term stability that complex life requires. The atmospheric pressure on K218b appears to fall within what astronomers now call the Goldilocks pressure range for hydrogen-rich worlds, substantial enough to maintain liquid water and efficient heat distribution, but not so intense as to create uninhabitable conditions. Current estimates suggest surface pressures between 2 times Earth's atmospheric pressure, comparable to the pressure experienced by deep-sea organisms on our own planet. This moderate pressure environment creates fascinating possibilities for atmospheric dynamics. Unlike the crushing depths of gas giant atmospheres, K218b's atmosphere might support complex weather systems with hydrogen and water vapor participating in atmospheric circulation patterns that could redistribute heat, moisture, and chemical compounds across the planet's surface. The hydrogen-helium composition also has profound implications for any potential life on K218b. Organisms on such a world would need to adapt to an atmospheric environment completely unlike anything on Earth. However, the presence of water vapor and moderate pressures suggests that the basic chemistry necessary for life, liquid water as a solvent, complex carbon-based molecules, and energy-driven chemical reactions, could still occur. One of the most intriguing aspects of K218b's atmospheric composition is what it reveals about the planet's formation and evolution. The retention of a substantial hydrogen-helium envelope suggests that K218b formed early in its system's history, when the protoplanetary disk still contained abundant light gases. The planet's core was massive enough to gravitationally capture and retain these gases, but not so massive as to run away accrete material and become a gas giant. The current atmospheric composition also indicates that K218b has avoided the atmospheric stripping that affects many planets orbiting close to their stars. Red dwarf stars, particularly young ones, can produce powerful stellar flares that gradually strip away planetary atmospheres over millions of years. The fact that K218b has retained its hydrogen-helium envelope suggests either that the star K218 is relatively quiet, or that the planet's atmosphere is massive enough to withstand stellar wind erosion. Recent atmospheric models suggest that the hydrogen-helium envelope might also provide protection against harmful radiation from space. The thick atmosphere could shield the planet's surface from cosmic rays and stellar particle radiation, creating a more benign environment for potential life than would exist on a planet with a thinner atmosphere. The Goldilocks problem of K218b's atmosphere, how hydrogen and helium create habitable rather than hostile conditions, represents a paradigm shift in our understanding of planetary atmospheres. It suggests that habitability might be possible under a much broader range of atmospheric conditions than we previously imagined, opening new possibilities for life in the cosmos. But the atmospheric story of K218b becomes even more intriguing when we consider the potential presence of gases that could be direct indicators of biological processes. Hidden within the spectroscopic data from K218b lies one of the most tantalizing and controversial detections in modern astronomy: the possible presence of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by living organisms. This detection, if confirmed, would represent the first potential biosignature ever discovered in the atmosphere of a habitable world beyond our solar system. Dimethyl sulfide, or DMS, is a sulfur-bearing organic molecule with the chemical formula CH8. On Earth, it's primarily produced by marine phytoplankton, algae, and certain bacteria as they break down organic matter in ocean environments. The molecule has a distinctive spectroscopic signature in the infrared spectrum, making it potentially detectable by sensitive space telescopes like JWST. The initial detection of what might be DMS in K218b's atmosphere sent shockwaves through the scientific community, but it also sparked intense debate about the reliability of the measurement. The spectroscopic feature that could indicate DMS appears at the very edge of detectability, requiring sophisticated statistical analysis to distinguish from instrumental noise and other atmospheric components. Dr. Niku Madhusudhan and his team at Cambridge University who led the atmospheric analysis of Cain-218b, approached the potential DMS detection with appropriate scientific caution. The feature appears in the data, but its statistical significance is marginal, strong enough to be intriguing, but not definitive enough to claim a confirmed detection. This uncertainty reflects the extraordinary challenge of detecting trace gases in exoplanet atmospheres across interstellar distances. If the DMS detection is real, its implications are profound. On Earth, dimethyl sulfide production is intimately linked to biological processes in marine environments. Ocean-dwelling phytoplankton produce DMS as they metabolize organic compounds, releasing the gas into the atmosphere, where it plays a role in cloud formation and climate regulation. The presence of DMS in Cain-218b's atmosphere could indicate similar biological processes occurring in the planet's hypothesized global ocean. However, the scientific community has learned to be cautious about potential biosignature detections. The history of astrobiology is littered with exciting discoveries that later proved to have non-biological explanations. The methane detection on Mars, initially thought to be a potential sign of life, has proven far more complex and ambiguous than originally hoped. Similarly, the phosphine detection in Venus's atmosphere, which generated enormous excitement in 2020, remains controversial and disputed. The challenge with interpreting the potential DMS detection lies in understanding whether non-biological processes could produce this molecule in Cain-218b's environment. While DMS is predominantly biological in origin on Earth, different planetary environments might allow for alternative formation pathways. Volcanic activity, atmospheric chemistry involving sulfur compounds, or interactions between the planet's atmosphere and surface could potentially produce DMS through purely geological processes. The atmospheric modeling team has explored various scenarios for DMS production on Cain-218b. If the planet truly is a Haitian world with a global ocean, the conditions might be remarkably similar to Earth's early oceans, where sulfur metabolizing organisms played crucial roles in atmospheric chemistry. The hydrogen-rich atmosphere could provide the reducing environment necessary for certain types of sulfur chemistry that might favor DMS production by hypothetical microorganisms. Another possibility is that DMS production on Cain-218b could result from entirely different biochemical pathways than those found on Earth. If life evolved independently on this alien world, it might have developed unique metabolic processes that produce familiar molecules through unfamiliar mechanisms. The different atmospheric composition and pressure conditions could favor biochemical reactions that are rare or impossible on Earth. The methane mystery extends beyond just DMS. The James Webb observations also search for other potential biosignature gases, including phosphine, ammonia, and various organic compounds that could indicate biological processes. While none of these other potential biosignatures have been detected in Cain-218b's atmosphere, the sensitivity limits of current observations mean that many biologically significant molecules could be present but remain below the detection threshold. The controversy surrounding the potential DMS detection highlights both the promise and the challenges of biosignature science. We now have the technological capability to search for signs of life in the atmospheres of potentially habitable exoplanets, but interpreting these detections requires unprecedented care and scientific rigor. False positives could set back the field of astrobiology by decades, while missing genuine biosignatures could delay one of the most important discoveries in human history. The methane mystery of Cain-218b remains unsolved, awaiting additional observations and more detailed atmospheric modeling. But regardless of whether DMS is confirmed, the mere possibility that we might be detecting the chemical signatures of alien life represents a watershed moment in our quest to understand our place in the universe. In the grand taxonomy of planets, Cain-218b occupies a mysterious middle ground that doesn't exist anywhere in our solar system. With a radius 2.6 times that of Earth and a mass roughly 8.6 times greater, it belongs to a category of worlds that astronomers have dubbed sub-Neptunes, planets that are too large to be considered super-Earths, but too small to be ice giants like Neptune. This cosmic in-between status makes K218b both familiar and utterly alien. To understand just how unusual sub-Neptunes are, consider the planetary lineup in our own solar system. We have small, rocky worlds like Mercury, Venus, Earth, and Mars, with radii ranging from 0.38 to 1.06 times Earth's radius. Then there's a vast gap, what astronomers call the Fulton Gap, before we reach the ice giants Uranus and Neptune, which are roughly 4 times Earth's radius. There's nothing in between. But when we look beyond our solar system, we discover that this gap is precisely where nature seems to prefer building planets. Sub-Neptunes, like K218b, are the most common type of planet in the galaxy, found orbiting roughly half of all Sun-like stars, surveyed by planet-hunting missions. The universe, it seems, has a preference for building worlds that are completely absent from our cosmic neighborhood. This prevalence raises profound questions about planetary formation. Why did our solar system fail to produce sub-Neptunes when they appear to be the galaxy's favorite planetary architecture? The answer might lie in the early history of our solar system and the specific conditions that prevailed during planetary formation around our Sun. Current theories suggest that sub-Neptunes form through a two-stage process. First, a solid core of rock, ice, and metal accumulates from the debris of a protoplanetary disk, similar to how terrestrial planets form. But unlike Earth, which stopped growing when it reached its current size, sub-Neptunes continue to accumulate material, eventually becoming massive enough to gravitationally capture significant atmospheres from the surrounding gas disk. The key is timing. Sub-Neptunes must reach sufficient mass to capture atmospheric gas before the protoplanetary disk dissipates, but they must avoid growing so large that they enter runaway gas accretion and become full gas giants. It's a narrow window of opportunity that requires precise conditions of disk lifetime, planetary core formation rate, and orbital location. K218b appears to represent the perfect execution of this formation process. Its core is substantial enough to have retained a significant atmospheric envelope for billions of years, but not so massive that it became a gas giant. The result is a world with roughly the same density as Neptune, about 1.2 times that of water, suggesting a composition that's part rock and ice, part atmospheric gas. The internal structure of sub-Neptunes, like K218b, remains one of astronomy's great puzzles. Models suggest these worlds might have layered structures unlike anything we know. At the center lies a rocky metallic core, perhaps 1.5-2 times the size of Earth, surrounded by a mantle of high-pressure ice and rock. Above this solid foundation stretches an atmospheric envelope of hydrogen, helium, and heavier molecules that might extend for thousands of kilometers above the surface. But here's where K218b becomes particularly intriguing. Its atmospheric envelope appears to be in the sweet spot for habitability. Many sub-Neptunes likely have atmospheres so thick that surface pressures reach thousands of times Earth's atmospheric pressure, creating conditions where familiar chemistry becomes impossible. Others might have lost their atmospheres entirely to stellar radiation, leaving behind barren super-Earth cores. K218b seems to have avoided both extremes. Its atmosphere is substantial enough to create greenhouse warming and weather systems, but not so thick as to crush surface conditions into uninhabitable extremes. This Goldilocks atmospheric mass might be the key to understanding why K218b earned its remarkable 99.7% habitability score. The sub-Neptune category also helps us understand why K218b can maintain liquid water despite orbiting a red dwarf star. The substantial atmospheric envelope acts as a thermal blanket, distributing heat around the planet and potentially preventing the tidal locking that would otherwise create extreme temperature variations between day and night sides. Recent research suggests that sub-Neptunes might represent nature's most efficient solution to the habitability challenge around red dwarf stars. These smaller, cooler stars have habitable zones that are much closer to the star than Earth's orbit around the Sun. Rocky planets in these close-in habitable zones face challenges from stellar radiation, tidal forces, and potential atmospheric stripping. But sub-Neptunes, with their substantial atmospheres and internal heat sources, might be better equipped to maintain habitable conditions in these challenging environments. The discovery of potentially habitable sub-Neptunes, like K218b, is revolutionizing astrobiology. Instead of looking exclusively for Earth twins, rocky planets orbiting sun-like stars, we're beginning to recognize that the most common potentially habitable worlds in the galaxy might be completely unlike Earth. They might be ocean worlds shrouded in hydrogen atmospheres, harboring life forms adapted to conditions we've never imagined. This paradigm shift has profound implications for estimating the prevalence of life in the universe. If sub-Neptunes can indeed be habitable, then the number of potentially life-bearing worlds in our galaxy increases by orders of magnitude. We're not limited to the rare Earth-like planets. We have access to an entire population of sub-Neptune ocean worlds that might be teeming with alien life. But to understand whether K218b truly represents a habitable sub-Neptune, we need to delve deeper into the extreme conditions that define these enigmatic worlds. Imagine descending into the deepest parts of Earth's oceans, where the weight of kilometers of water above creates pressures that would instantly crush any surface-dwelling organism. Now imagine living your entire existence under such conditions, but instead of crushing ocean depths, you're surrounded by a thick atmosphere of hydrogen and water vapor. This is the reality that any potential life on K218b would face, a high-pressure environment that challenges our fundamental assumptions about habitability. The atmospheric pressure on K218b represents one of the most critical unknowns in assessing its habitability potential. Early models of sub-Neptune atmospheres suggested crushingly dense gas envelopes that would create surface pressures hundreds or thousands of times greater than Earth's atmosphere. Under such conditions, water couldn't exist as a liquid. It would be compressed into exotic high-pressure ice phases, or exist as supercritical fluid that behaves neither as liquid nor gas. But the James Webb Space Telescope observations suggest a different scenario. The spectroscopic signatures from K218b's atmosphere indicate a more moderate pressure environment, substantial enough to maintain liquid water and efficient heat distribution, but not so extreme as to preclude habitability entirely. Current estimates place the surface pressure between 2 and 10 times Earth's atmospheric pressure, comparable to the conditions experienced by deep-sea life on our own planet. This pressure range opens fascinating possibilities for understanding habitability under extreme conditions. On Earth, life thrives in high-pressure environments. In the deepest ocean trenches, where pressures reach over 1,000 times atmospheric pressure, complex ecosystems flourish around hydrothermal vents. Organisms called piezophiles have evolved specifically to live under high-pressure conditions, with cellular structures and biochemistry adapted to function where surface life would be instantly destroyed. The moderate high-pressure environment of K218b might actually enhance certain aspects of habitability. Higher atmospheric pressure increases the boiling point of water, allowing liquid water to exist at higher temperatures than would be possible under Earth-like pressure conditions. This extended temperature range for liquid water could create more diverse environmental niches for potential life. The composition of K218b's high-pressure atmosphere also matters enormously for habitability. The hydrogen-rich environment would create a reducing atmosphere, the opposite of Earth's oxygen-rich oxidizing atmosphere. In reducing conditions, different types of chemistry become possible. Many of the chemical reactions that might have been crucial for the origin of life on early Earth occurred under reducing conditions, before photosynthesis filled our atmosphere with oxygen. A hydrogen-rich, high-pressure atmosphere could provide energy sources for life through chemical processes that don't occur under Earth-like conditions. Hydrogen itself can serve as an energy source for certain types of organisms called hydrogenotrophs, which derive energy by combining hydrogen with other chemicals. In the dense atmosphere of K218b, such organisms might have access to vast quantities of hydrogen fuel. The water vapor present in this high-pressure environment adds another layer of complexity. Water vapor under pressure behaves differently than under Earth-like conditions. potentially facilitating chemical reactions that could be important for biological processes. The combination of hydrogen, water vapor, and moderate high pressure might create a unique chemical environment where life could evolve along completely different pathways than terrestrial biology. However, high pressure also presents significant challenges for life, as we understand it. The increased pressure affects the folding and function of complex molecules like proteins and DNA. Cellular membranes must be reinforced to maintain their integrity under pressure. The physics of gas diffusion, chemical reaction rates, and molecular interactions all change under high-pressure conditions. Perhaps most intriguingly, the high-pressure environment of K218b might favor the formation and stability of complex organic molecules that are crucial for life. Under certain pressure and temperature conditions, amino acids, nucleic acids, and other biological building blocks can form more readily and remain stable for longer periods. The compressed atmosphere might act as a natural laboratory for prebiotic chemistry. The pressure cooker question also relates to the planet's ability to maintain its atmospheric envelope over geological time. The moderate high pressure inferred from observations suggests that K218b has successfully retained its atmosphere despite billions of years of stellar wind erosion and potential impact events. This atmospheric retention is crucial for long-term habitability. Life needs stable environmental conditions over the extended periods required for evolution and development. Understanding the pressure environment on K218b is crucial for assessing not just whether life could exist there, but what forms it might take. The answer to the pressure cooker question will determine whether we're looking at a world of extremophiles adapted to crushing conditions, or a more benign environment where familiar biochemistry could operate under slightly modified conditions. In TWE, the answer to the pressure cooker question will determine Neverinium and 4 useful for assessing not just whether life could exist there, but what forms it might take. But pressure is only one piece of the habitability puzzle. To truly understand K218b's potential for life, we must consider the possibility that this world is covered by a global ocean unlike anything in our solar system. Picture a world where the horizon in every direction reveals nothing but endless ocean, no continents, no islands, no land masses of any kind. The entire surface of the planet is covered by water that stretches to depths that dwarf Earth's deepest trenches, beneath an alien sky thick with hydrogen and water vapor. This is the vision of K218b as a Haitian world, a hydrogen atmosphere ocean planet that represents an entirely new category of potentially habitable environment. The concept of K218b as a global ocean world emerged from attempts to reconcile the planet's physical characteristics with its observed atmospheric composition, with 2.6 times Earth's radius and 8.6 times its mass. K218b has an average density of about 2.3 grams per cubic centimeter, significantly less dense than Earth's 5.5 grams per cubic centimeter. This low density suggests that a substantial fraction of the planet's mass consists of lighter materials, most likely water and atmospheric gases. Current models propose a layered structure that reads like science fiction, but represents our best understanding of sub-Neptune architecture. At the center lies a rocky metallic core, perhaps 1.2 to 1.5 times Earth's radius, containing the heavy elements necessary for planetary formation. Surrounding this core is a mantle layer that might consist of high-pressure ice, liquid water, or exotic phases of H2O that exist only under extreme conditions. But the most remarkable layer is the outermost one, a global ocean that could be hundreds or even thousands of kilometers deep. To put this in perspective, Earth's average ocean depth is less than 4 kilometers, with the deepest point reaching just over 11 kilometers. Hormeters, or view of Nobik Pisin. Hormetamar, the ocean on K218b might be 100 times deeper than any terrestrial ocean, containing more water than has ever existed on Earth throughout its entire history. The physics of such a deep ocean would be unlike anything we know. In the deepest regions, water would exist under pressures millions of times greater than at Earth's surface. potentially forming exotic high-pressure phases of ice that remain solid despite temperatures that would boil water under normal conditions. The pressure gradient from the ocean surface to its depths would create distinct layers with different physical and chemical properties, each potentially harboring different types of life. The interface between this global ocean and the hydrogen-rich atmosphere above represents one of the most intriguing environments for potential life. Unlike Earth's oceans, which are exposed to space and vulnerable to evaporation and atmospheric loss, K218b's ocean would be protected by a thick atmospheric blanket that prevents water loss while maintaining temperate surface temperatures through greenhouse warming. The chemical composition of this alien ocean remains largely speculative, but the presence of substantial water vapor in the atmosphere provides important clues. For water to exist as vapor in the atmosphere, it must be continuously evaporating from the ocean surface, indicating active weather systems with evaporation, cloud formation, and precipitation occurring on a planetary scale. This water cycle could distribute nutrients, chemicals, and potentially even microorganisms throughout the ocean system. The salinity and chemical composition of K218b's ocean would likely be very different from Earth's seawater. The extended contact between water and the rocky core under high pressure and temperature conditions could dissolve substantial quantities of minerals and create chemical environments that don't exist in Earth's oceans. These chemical differences could provide energy sources for exotic forms of life, or create conditions where familiar biochemistry operates in unfamiliar ways. One of the most intriguing aspects of a Haitian ocean world is the potential for vertical zonation of life. On Earth, ocean life is stratified by depth, with different organisms adapted to different pressure, temperature, and light conditions at various depths. On K218b, the extreme depth of the global ocean could create numerous distinct ecological zones, each with its own unique conditions and potential life forms. Near the surface, organisms might exist in relatively familiar conditions, liquid water at moderate pressures under a hydrogen-rich sky. The reducing atmosphere could support chemosynthetic organisms that derive energy from chemical reactions rather than photosynthesis. Without oxygen in the atmosphere, any photosynthesis would need to use different chemical pathways, potentially producing methane, hydrogen sulfide, or other reduced compounds instead of oxygen. In the middle depths of the ocean, life might adapt to higher pressures and different chemical gradients. The interaction between the hydrogen atmosphere and the ocean could create unique chemical environments where hydrogen metabolizing organisms could thrive, using the abundant atmospheric hydrogen as an energy source in ways that aren't possible in Earth's oxygen-rich environment. In the deepest regions of the ocean, near the interface with the solid planetary interior, hydrothermal activity could provide energy sources similar to those that support deep-sea ecosystems on Earth. The circulation of water through the rocky interior could create hydrothermal vents that supply heat and chemical energy to support ecosystems completely independent of stellar energy input. The global nature of KT218b's hypothesized ocean also means that any life that evolved there would have access to a much larger and more connected habitat than life on Earth. Our planet's oceans are divided by continents and varying depths, creating barriers to the spread of organisms and the mixing of nutrients. KT218b's global ocean would be a single connected ecosystem where currents could circulate materials and organisms around the entire planet. The stability of such an ocean world over geological timescales is another crucial factor for habitability. Unlike terrestrial planets, where oceans can freeze or evaporate depending on climatic conditions, K218b's ocean would be protected by its substantial atmosphere and maintained by the planet's internal heat. This stability could provide the long-term environmental consistency necessary for complex life to evolve over billions of years. The possibility that K218b harbors a global ocean has profound implications for astrobiology and our search for life beyond Earth. Ocean worlds might be far more common in the universe than Earth-like terrestrial planets, potentially making water-based life more prevalent than we ever imagined. If K218b does indeed harbor a global ocean beneath its hydrogen-rich atmosphere, it would represent not just a new type of habitable world, but a new paradigm for understanding where and how life might exist in the cosmos. But to appreciate how remarkable K218b's potential ocean world truly is, we need to understand the unique advantages that its red dwarf star provides, advantages that might make ocean worlds around small stars the most likely places to find life in the universe. 1. In the cosmic hierarchy of stars, red dwarfs like Cav 218 are the universe's humble workhorses, small, dim, and easily overlooked. They produce less light in a year than our sun generates in a day. They're so faint that even the closest red dwarf to Earth, Proxima Centauri, is invisible to the naked eye, despite being only 4.2 light-years away. Yet these unassuming stellar embers might harbor more potentially habitable worlds than all other types of stars combined. The red dwarf advantage begins with sheer numbers. Roughly 75% of all stars in our galaxy are red dwarfs, making them by far the most common type of star in the universe. While massive, brilliant stars capture our attention and imagination, red dwarfs represent the statistical norm. In our local galactic neighborhood, red dwarfs outnumber sun-like stars by more than 3 to 1, creating a vast population of potential planetary hosts that astronomers have only recently begun to fully appreciate. K218 exemplifies the characteristics that make red dwarfs compelling targets for habitability studies. With roughly half the mass of our Sun and about 2.3% of its luminosity, K218 burns its nuclear fuel so slowly that it will continue shining for over 1 trillion years, more than 70 times longer than our Sun's expected lifetime. This extraordinary longevity provides unprecedented opportunities for biological evolution. While life on Earth has had roughly 4 billion years to evolve from simple chemicals to complex organisms, life around red dwarfs like K218 could have trillions of years to develop. The implications of this extended time frame are staggering. Evolution on Earth has produced remarkable diversity and complexity in just 4 billion years. But imagine what could evolve given 250 times longer. Red dwarf systems represent cosmic laboratories where evolution could experiment with biological forms and ecosystems that are simply impossible within the constraints of shorter-lived stellar systems. The small size and low mass of red dwarfs also create ideal conditions for planet detection and atmospheric study. When a planet transits across a red dwarf star, it blocks a larger percentage of the star's light than would occur with a larger, brighter star. This enhanced contrast makes it easier to detect planets and, crucially, to study their atmospheres through transit spectroscopy. The James Webb Space Telescope's detailed analysis of K218b's atmosphere was possible precisely because the planet orbits a small, dim red dwarf rather than a sun-like star. The habitable zones around red dwarfs present both opportunities and challenges that are reshaping our understanding of planetary habitability. Because red dwarfs produce less energy than larger stars, their habitable zones are much closer to the star, typically between 0.1 and 0.2 astronomical units, compared to Earth's distance of 1 astronomical unit from the Sun. This proximity means that planets in the habitable zone experience stronger gravitational forces from their star, potentially leading to tidal locking, where one side of the planet permanently faces the star. However, recent research suggests that tidal locking might not be the habitability killer once assumed. Planets with substantial atmospheres, like K218b, could redistribute heat efficiently enough to prevent extreme temperature differences between day and night sides. The thick hydrogen-rich atmosphere of a sub-Neptune could act as a thermal blanket, maintaining temperate conditions across the entire planetary surface, despite tidal locking. The spectral characteristics of red dwarf stars also have profound implications for potential life. Red dwarfs emit most of their energy in the near-infrared spectrum, creating a fundamentally different energy environment than the visible light-dominated output of stars like our Sun. This has led to speculation about infrared photosynthesis, biological processes that could harvest energy from the infrared-rich light of red dwarf stars. Ivsiki, from the Gendaji, 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 from the Gendaji. On Earth, photosynthesis has evolved to utilize the visible light spectrum that our sun produces most abundantly. But around red dwarfs, evolution might favor organisms that can efficiently capture and utilize near-infrared radiation. Such organisms might appear black or dark to human eyes, absorbing across broader wavelength ranges to maximize energy capture from their dim host stars. The metallicity of red dwarfs, their abundance of elements heavier than hydrogen and helium, varies significantly throughout the galaxy. K218 has a metallicity similar to our Sun, indicating that it formed from material enriched by previous generations of stars. This metal content is crucial for forming rocky planetary cores and supporting the complex atmospheric chemistry that appears to make K218b potentially habitable. The red dwarf advantage extends to planetary system architecture. Many red dwarf systems contain multiple planets in compact configurations, with several worlds orbiting within the distance that Mercury orbits our Sun. These tightly packed systems create opportunities for gravitational interactions that could enhance habitability through tidal heating, magnetic field generation, and atmospheric exchange between planets. Thopiro Sibia Zeroia Vitria Zeroia Vitrias. Night Sorvamidu Surya Zeroia Vitrias. Perhaps most significantly, red dwarfs represent the future of habitability in our universe. As more massive stars exhaust their fuel and die, red dwarfs will become increasingly dominant. In the far future of our galaxy, when star formation has nearly ceased and most massive stars have long since burned out, red dwarfs will continue to shine, potentially supporting life for trillions of years after stars like our Sun have become cold white dwarf remnants. Insurices, Os, Kuv. Nabikandel Funav that Pars. The red dwarf advantage suggests that we may be living in a universe where the most common potentially habitable worlds orbit the smallest, dimmest, most long-lived stars. K218b might represent not an exotic exception, but rather a glimpse of the most typical kind of habitable world in the cosmos. Understanding this advantage is crucial for appreciating why the discovery of K218b is so significant, and why its host star's tendency towards stellar outbursts presents both challenges and opportunities for life. The tranquil image of K218b as a peaceful ocean world beneath a hydrogen sky is occasionally shattered by one of the most violent phenomena in astronomy, stellar flares. These explosive releases of energy from the surface of red dwarf stars can unleash more energy in minutes than human civilization has used throughout its entire history, bathing nearby planets in deadly radiation that could strip away atmospheres and sterilize surfaces. Red dwarf stars are notorious for their flaring activity, particularly when they're young. These stellar outbursts occur when magnetic field lines in the star's atmosphere become tangled and suddenly reconnect, releasing vast amounts of stored magnetic energy in the form of X-rays, ultraviolet radiation, high-energy particles. For planets orbiting close to red dwarfs, as all habitable zone planets must, these flares represent a serious challenge to maintaining the conditions necessary for life. The flare factor was once considered a deal-breaker for red dwarf habitability. Early models suggested that the intense radiation from stellar flares would gradually strip away planetary atmospheres through a process called atmospheric erosion. High-energy particles from flares would collide with atmospheric molecules, giving them enough energy to escape the planet's gravitational pull. Over millions of years, this process could transform a potentially habitable world into a barren, airless rock. K218, however, appears to be what astronomers call a quiet red dwarf. Observations spanning several years have detected only modest flaring activity from this star, suggesting that it has settled into a stable, mature phase of its evolution. The star's age, approximately 2.3 billion years, places it beyond the most violent flaring period that characterizes young red dwarfs. This relative quietude has likely been crucial for KAU 218b's ability to maintain its substantial atmosphere over geological time. But even quiet red dwarfs produce occasional flares, and the effects of these events on KAU 218b would be dramatic. When a flare erupts from KAU 218, the planet would be bathed in a flood of high-energy radiation within minutes. The upper atmosphere would heat rapidly, potentially causing it to expand and increasing the rate of atmospheric loss to space. Any organisms living in the ocean's surface layers would be exposed to lethal doses of ultraviolet and X-ray radiation. However, KAU 218b's substantial atmosphere might actually provide protection against flare activity. The thick hydrogen envelope could absorb much of the harmful radiation before it reaches the ocean's surface, acting as a natural radiation shield. While the upper atmosphere might be heated and partially stripped away during major flares, the bulk of the atmospheric mass would remain intact, and the atmosphere could potentially recover between flare events. The hydrogen-rich composition of KAU 218b's atmosphere also affects how it responds to stellar radiation. Hydrogen molecules can absorb and re-emit energy efficiently, potentially helping to dissipate the heat generated during flare events. This could prevent the runaway heating that might occur in atmospheres with different compositions, helping to maintain stable conditions despite occasional stellar outbursts. Recent research has even suggested that stellar flares might have positive effects on habitability under certain circumstances. The high-energy radiation from flares can drive atmospheric chemistry that produces organic compounds, the building blocks of life. Lightning during storms on Earth serves a similar function, using electrical energy to forge complex molecules from simple atmospheric gases. Stellar flares could provide the energy necessary to jumpstart prebiotic chemistry in the atmospheres of red dwarf planets. The flare factor also affects the type of life that could potentially exist on KAU 218b. Any organisms in the planet's ocean would need to be adapted to periodic radiation events, possibly living at depths that provide natural shielding or possessing enhanced DNA repair mechanisms to survive radiation damage. Life on such worlds might be dominated by organisms similar to Earth's extremophiles, hardy microorganisms that thrive in conditions that would be lethal to more complex life forms. The radiation environment around red dwarfs might also influence the evolution of life in unexpected ways. On Earth, the relatively stable radiation environment provided by our Sun has allowed life to evolve complex, radiation-sensitive organisms. Around flaring red dwarfs, evolution might favor organisms with enhanced radiation resistance, potentially leading to biological forms that are far more robust than terrestrial life. Understanding the flare factor is crucial for assessing the long-term habitability of KAU 218b and similar worlds. While stellar flares present significant challenges, they are not necessarily fatal to habitability. The key lies in understanding how planetary atmospheres, magnetic fields, and potential biospheres can adapt to and even benefit from the variable radiation environment around red dwarf stars. The flare factor represents just one aspect of the complex relationship between KAU 218b and its host star, a relationship that has been shaped by billions of years of stellar and planetary evolution. The story of KAU 218 and its remarkable planet unfolds across a time span so vast that it challenges human comprehension. At approximately 2.3 billion years old, the KAU 218 system has already existed for half the age of our entire universe, yet it's barely begun its cosmic journey. This is a 10 billion year story, a tale of stellar evolution, planetary development, and potentially biological evolution occurring on timescales that dwarf the entire history of complex life on Earth. When KAU 218 first ignited nuclear fusion in its core, 2.3 billion years ago, our own solar system was already ancient by comparison. The sun had been shining for more than 2 billion years. and early life was just beginning to transform Earth's atmosphere through the emergence of photosynthesis. Meanwhile, in the constellation Leo, a new red dwarf was beginning its extraordinary journey through cosmic time. The early years of the K218 system would have been chaotic and violent. Young red dwarfs are notorious for their intense flaring activity, producing stellar outbursts, far more powerful and frequent than those seen from mature red dwarf stars. During this tumultuous period, any planets in the system would have been subjected to intense bombardments of high-energy radiation. Many planetary scientists believe that this early flaring epoch would have been fatal to any existing atmospheres, stripping away the gas envelopes that planets like K218b need to maintain habitable conditions. Yet somehow, K218b survived this violent youth, with its atmosphere intact. This survival suggests several intriguing possibilities about the planet's formation and early evolution. K218b might have formed with such a massive atmospheric envelope that even significant losses during the early flaring period left enough atmosphere to maintain habitability. Alternatively, the planet might have continued to outgas volatile materials from its interior, replenishing atmospheric losses faster than stellar activity could strip them away. The transition of K218 from a young, active flare star to a mature, relatively quiet, red dwarf marks a crucial turning point in the system's habitability story. As the star settled into stable hydrogen burning, the radiation environment around K218b would have become much more benign, creating the conditions necessary for complex atmospheric chemistry and potentially biological evolution to proceed. This stabilization occurred roughly 1.5–2 billion years ago, coincidentally around the same time that complex cells were evolving on Earth. If life did emerge on K218b during this period, it would have had nearly 2 billion years to evolve and diversify, roughly half the time that life has existed on Earth, but still an enormous span for biological development. The remarkable aspect of K218's evolutionary story is what lies ahead. While our Sun is already middle-aged and will begin its death throes in about 5 billion years, K218 has barely begun its main sequence lifetime. Red dwarfs burn their nuclear fuel so efficiently that they can continue producing energy for trillions of years. K218 will still be shining long after our Sun has expanded into a red giant, expelled its outer layers, and cooled to a white dwarf remnant. This extraordinary longevity has profound implications for any potential life in the K218 system. Evolution on Earth has produced remarkable complexity in roughly 4 billion years, transforming simple chemical systems into organisms capable of consciousness, technology, and space exploration. Given trillions of years of stable stellar energy, evolution around red dwarfs like K218 could potentially produce forms of life and intelligence that are literally inconceivable to us. The 10 billion year perspective also reveals the true significance of sub-Neptune worlds like K218b in the cosmic context. While Earth-like terrestrial planets might represent brief experiments in habitability around short-lived Sun-like stars, sub-Neptunes around red dwarfs could be the universe's long-term solution to the challenge of maintaining life over cosmic time. These worlds combine the atmospheric stability necessary to weather stellar evolution with the longevity to support biological evolution on unprecedented timescales. Current models of stellar evolution suggest that K218 will remain virtually unchanged for the next several trillion years. The star's luminosity will increase only gradually, and its habitable zone will expand slowly outward. This stability means that K218b will remain within the habitable zone for periods that make the entire history of complex life on Earth seem like a brief moment. The chemical evolution of the K218 system over these vast timescales also presents intriguing possibilities. The gradual nuclear processing within K218's core will slowly change the star's composition and energy output. Meanwhile, geological processes on K218b, if it indeed harbors a global ocean, could continue to evolve the planet's atmospheric and oceanic chemistry over billions of years. The interplay between stellar evolution, planetary geology, and potentially biological processes could create environmental changes and opportunities for evolution that are impossible to predict, but fascinating to consider. Perhaps most remarkably, the 10 billion year story of K2-18 represents just the beginning. When our sun has been dead for longer than it has been alive, K2-18 will still be a young star with most of its hydrogen fuel remaining. The system could potentially support life for periods that exceed the current age of the universe by orders of magnitude. This cosmic perspective transforms our understanding of K2-18b's 99.7% habitability score. We're not just looking at a world that might harbor life today, we're looking at a planetary system with the potential to support life and evolution for periods that stretch the limits of imagination. Understanding this temporal dimension is crucial for appreciating why red dwarf systems like K2-18 might represent the future of life in our universe. Discovering Dia might represent the future of life in our universe. Understanding this temporal dimension is crucial for appreciating why red dwarf system networks. Understanding this temporal dimension is crucial for appreciating why red dwarf systems like K2-18 might represent the future of life in our universe. But to fully understand K2-18b's significance, we must examine the revolutionary technology that made its discovery possible, technology that is transforming our ability to study potentially habitable worlds across the galaxy. In the deep cold of space, 1.5 million kilometers from Earth, floats humanity's most powerful window into the cosmos. The James Webb Space Telescope, with its golden hexagonal mirror spanning 6.5 meters, has revolutionized our ability to peer into the atmospheres of distant worlds and detect the chemical signatures that could indicate life beyond our solar system. The discovery and detailed analysis of K2-18b's potentially habitable atmosphere represents one of the most stunning achievements of this technological marvel. To understand the magnitude of JWST's accomplishment in studying K2-18b, consider the challenge involved. We're attempting to analyze the atmospheric composition of a world 124 light-years away, a distance so vast that light from K2-18b left the planet during the late 19th century and is only now reaching our telescopes. The planet itself is invisible to direct observation, hidden in the glare of its host star. Yet somehow, JWST has managed to detect water vapor, carbon dioxide, and potentially even biosignature gases in this alien atmosphere. The secret lies in a technique called transit spectroscopy, a method so elegant in concept, yet so challenging in execution, that it represents one of the pinnacles of astronomical instrumentation. When K2-18b passes between its star and Earth, an event that occurs every 33 days and lasts about 3 hours, starlight filters through the planet's atmosphere before reaching our telescopes. Different molecules in the atmosphere absorb specific wavelengths of this starlight, creating a unique spectroscopic fingerprint that reveals the atmospheric composition. But the challenge is immense. The atmospheric signal from K2-18b represents a change in starlight intensity of less than 0.01%, equivalent to detecting the shadow cast by a fruit fly crossing in front of a lighthouse beam from hundreds of miles away. This infinitesimal signal must be extracted from noise created by atmospheric turbulence, instrumental effects, and the natural variability of the star itself. It requires measurement precision that pushes the absolute limits of what's technologically possible. JWST's revolutionary capabilities stem from its unprecedented combination of mirror size, thermal sensitivity, and wavelength coverage. The telescope's primary mirror collects more than 6 times as much light as the Hubble Space Telescope, providing the photon gathering power necessary to detect these faint atmospheric signals. But equally important is JWST's position at the second Lagrange point, where it operates in the deep cold of space, far from Earth's thermal interference. The telescope's 4 scientific instruments work together to dissect the light from K2-18b's atmosphere with extraordinary precision. The near-infrared spectrograph, NIRIN-SPEC, provides high-resolution spectroscopy that can detect individual molecular absorption lines. The near-infrared imager and slitless spectrograph, NIRINS offers broad wavelength coverage optimized for atmospheric studies. The mid-infrared instrument, NIRINS SPEC, extends observations into longer wavelengths, where many molecules produce their strongest absorption features. The data processing required to extract atmospheric information from these observations represents a triumph of computational astronomy. Raw telescope data must be carefully calibrated to remove instrumental effects. Stellar variability must be modeled and subtracted, and systematic errors must be identified and corrected. The final atmospheric spectrum emerges from this process like a hidden message decoded from cosmic noise. What makes JWST's analysis of K218b particularly remarkable is the depth and breadth of atmospheric information it has revealed. Previous space telescopes could detect the presence of water vapor in hot Jupiter atmospheres, massive gas giants orbiting close to their stars, where atmospheric signals are strong and relatively easy to detect. But K218b represents a much more challenging target, a smaller, potentially habitable world orbiting a dim red dwarf star. The telescope's infrared sensitivity is crucial for studying red dwarf planetary systems. Red dwarf stars emit most of their energy in near-infrared wavelengths, and the atmospheric molecules we're most interested in, water vapor, carbon dioxide, methane, and potential biosignatures, produce their strongest absorption features in the infrared spectrum. JWST's ability to observe these wavelengths with unprecedented sensitivity makes it the perfect instrument for characterizing potentially habitable worlds around the most common stars in our galaxy. The precision achieved in K218b's atmospheric analysis represents a quantum leap beyond previous capabilities. Earlier studies of exoplanet atmospheres could detect the presence or absence of major atmospheric components. JWST's observations of K218b not only confirm the presence of water vapor and carbon dioxide, but provide information about their relative abundances, vertical distribution in the atmosphere, and temperature and pressure conditions at different atmospheric levels. Perhaps most remarkably, JWST's observations hint at the presence of dimethyl sulfide in K218b's atmosphere, a molecule that on Earth is produced almost exclusively by living organisms. While this detection remains at the edge of statistical significance and requires confirmation, the mere possibility that we might be detecting biosignature gases in the atmosphere of a potentially habitable exoplanet represents a watershed moment in astronomy. The technological achievement represented by JWST's study of K218b extends far beyond a single observation. The techniques and capabilities demonstrated in this analysis are now being applied to dozens of other potentially habitable worlds. The telescope is systematically studying the atmospheres of rocky planets in the habitable zones of nearby red dwarf stars, sub-Neptunes like K218b, that might harbor global oceans, and even some terrestrial planets around sun-like stars. Each new observation adds to our growing understanding of atmospheric diversity on exoplanets and expands our definition of habitability. JWST is revealing that planetary atmospheres are far more diverse and complex than we ever imagined, with chemical compositions and physical conditions that challenge our Earth-centric assumptions about habitability. The revolution in exoplanet atmospheric studies is just beginning. JWST's observations of K218b required only a few transits and a handful of hours of telescope time. Future observations will accumulate dozens of transits, providing the statistical precision necessary to detect even fainter atmospheric features and potential biosignatures. The telescope's planned 10-year mission lifetime will allow for long-term monitoring of atmospheric changes and seasonal variations on potentially habitable worlds. The technological capabilities that made K218b's atmospheric analysis possible represent humanity's first serious attempt to chemically analyze potentially habitable worlds around other stars. This achievement transforms the search for extraterrestrial life from speculation to observational science, providing the tools necessary to answer one of the most profound questions in science: are we alone in the universe? But to fully appreciate the significance of JWST's observations, we need to understand the elegant physics behind spectroscopy. the technique that allows us to decode the chemistry of alien worlds from starlight. In 1802, a German physicist named Joseph von Fraunhofer made an observation that would eventually allow us to analyze the atmosphere of a world orbiting a star 124 light-years from Earth. While studying sunlight through a prism, Fraunhofer noticed hundreds of dark lines crossing the rainbow spectrum, mysterious gaps in the sun's light that seemed to appear at specific wavelengths. He had no way of knowing that he was seeing the first evidence of the sun's chemical composition, encoded in starlight through the fundamental physics of atomic absorption. Spectroscopy, the analysis of light across different wavelengths, has become astronomy's most powerful tool for understanding the universe. Those dark lines that puzzled Fraunhofer are now understood as absorption features, created when atoms and molecules absorb specific wavelengths of light, each element and compound producing its own unique spectroscopic fingerprint. This cosmic barcode allows us to determine not just what distant objects are made of, but their temperatures, pressures, and even motion through space. The application of spectroscopy to exoplanet atmospheres represents one of the most technically challenging observations in astronomy. When Ki 218b transits across its star, we're not directly observing the planet's light. We're analyzing how the planet's atmosphere modifies starlight as it passes through. It's like trying to identify the ingredients in a recipe by tasting a single grain of salt that fell into a swimming pool. The physics behind this technique relies on the quantum mechanical properties of atoms and molecules. When a photon of light encounters an atom or molecule, it can be absorbed if its energy precisely matches the difference between two energy levels in that atom or molecule. Different substances have different energy level structures, so they absorb light at different wavelengths, creating unique spectroscopic signatures. Water vapor, one of the key molecules detected in K218b's atmosphere, produces absorption features at several specific wavelengths in the near-infrared spectrum. These features occur because water molecules can rotate and vibrate in specific ways, each motion corresponding to a particular energy level transition. When infrared light with the right wavelength encounters a water molecule, the photon's energy excites the molecule to a higher rotational or vibrational state, removing that wavelength from the transmitted light. The detection of water vapor in K218b's atmosphere required identifying these characteristic absorption features in the modified starlight observed during transits. But the challenge goes far beyond simply looking for dark lines in a spectrum. The atmospheric signal from K218b represents a change in the star's brightness of less than 100 parts per million, a variation so small that it requires extraordinary precision to detect and measure accurately. With details of Crawdmere, this calm Asperius to Porphyria Cinctura. The process begins with careful observation of K218b's star during and outside of transit events. When the planet is not transiting, all the starlight we observe comes directly from the star. During a transit, a tiny fraction of that light passes through the planet's atmosphere before reaching us. By comparing these two observations and looking for wavelength-dependent differences, astronomers can extract the atmospheric transmission spectrum, a graph showing how much light the atmosphere absorbs at each wavelength. The atmospheric transmission spectrum of K218b reveals the telltale signatures of multiple molecules. Water vapor creates broad absorption features around 1.4 and 1.9 micrometers. Carbon dioxide produces a distinctive signature near 2.0 micrometers. The potential detection of dimethyl sulfide relies on much weaker features that push the limits of current observational capabilities. But spectroscopy provides more than just molecular identification. The shape and depth of absorption features reveal information about atmospheric temperature and pressure profiles. Strong, broad absorption features indicate high concentrations of absorbing molecules, while narrow features suggest lower concentrations or specific atmospheric conditions. The precise wavelength positions of absorption lines can reveal atmospheric motion, winds, rotation, and large-scale circulation patterns. The interpretation of K218b's spectrum required sophisticated atmospheric models that account for the complex physics of radiative transfer in hydrogen-rich atmospheres. These models must consider how light scatters and absorbs as it passes through atmospheric layers with different temperatures, pressures, and compositions. The process is iterative. Scientists compare observed spectra with model predictions, adjust the atmospheric parameters in their models, and repeat until they find the combination of conditions that best explains the observations. One of the most remarkable aspects of spectroscopic analysis is its ability to detect trace gases that make up tiny fractions of an atmosphere. The potential detection of dimethyl sulfide in K2-18b's atmosphere, if confirmed, would involve a molecule that might comprise less than 1 part per billion of the atmospheric composition. Yet the exquisite sensitivity of modern spectroscopic techniques makes such detections theoretically possible. The spectroscopic analysis of K2-18b also demonstrates the power of combining observations across multiple wavelengths. Different molecules produce their strongest absorption features at different wavelengths, so comprehensive atmospheric characterization requires observations spanning a broad spectral range. JWST's ability to observe from 0.7 to 28 micrometers allows it to detect a wide variety of atmospheric constituents and provide a complete picture of atmospheric composition. The Rosetta Stone allowed archaeologists to decode Egyptian hieroglyphics by providing the same text in multiple languages. Spectroscopy serves as the Rosetta Stone of space, allowing us to decode the chemical messages written in starlight and understand the composition of worlds we will never visit. Through this elegant technique, we can analyze alien atmospheres, search for biosignatures, and take the first steps toward answering the ultimate question: are we alone in the universe? The spectroscopic data that revealed K2-18b's remarkable atmosphere represents more than just a technical achievement. It's a glimpse into a new era of astronomy where we can study the chemistry of potentially habitable worlds across the galaxy. On October 11, 2023, the journal Astronomy and Astrophysics published a paper that would fundamentally alter our understanding of habitability beyond our solar system. Titled Carbon-Bearing Molecules in a Possible Haitian Atmosphere, the study presented 27 pages of spectroscopic analysis that transformed K2-18b from an interesting exoplanet into the most compelling potentially habitable world ever discovered. The data behind this revolutionary paper came from just 2 transit observations of K2-18b by the James Webb Space Telescope, totaling fewer than 8 hours of telescope time. Yet these observations contained more information about the atmosphere of a potentially habitable exoplanet than had been gathered in the entire previous history of astronomy. The precision and depth of the spectroscopic measurements represented a quantum leap in our ability to characterize alien worlds. The breakthrough began with the water vapor detection, a signal so strong and unambiguous that it immediately established K2-18b as an exceptional world. Previous studies had hinted at the presence of water vapor in the planet's atmosphere, but JWST's observations revealed water absorption features with unprecedented clarity and precision. The strength of these features indicated that water vapor makes up a significant fraction of the atmospheric composition, far more than would be expected from trace amounts of atmospheric moisture. But it was the detection of carbon dioxide that truly began to revolutionize our understanding of K2-18b. The CO2 absorption features appeared at exactly the wavelengths predicted by atmospheric models, with strengths that indicated substantial concentrations of this molecule in the planet's atmosphere. The presence of both water vapor and carbon dioxide suggested complex atmospheric chemistry and potentially active weather systems involving both molecules. The data analysis revealed subtle but crucial details about the atmospheric structure of K2-18b. The shape and depth of the absorption features indicated that water vapor and carbon dioxide are distributed throughout much of the atmosphere, not concentrated in thin layers near the surface. This vertical distribution pattern was consistent with a moderate atmospheric envelope rather than the crushing, thick atmosphere that many theoretical models had predicted for sub-Neptune worlds. Perhaps most remarkably, the data hinted at the presence of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by living organisms. The potential DMS detection appeared as weak absorption features at the very edge of the telescope's sensitivity limits, requiring sophisticated statistical analysis to distinguish from instrumental noise. While the detection remains tentative and requires confirmation, its mere possibility represents a watershed moment in astrobiology. The absence of certain expected atmospheric components proved as significant as the detections themselves. The data showed no clear evidence of ammonia, which would be expected in substantial concentrations if K218b had a thick, hydrogen-rich atmosphere similar to Neptune. This absence supported models suggesting a more moderate atmospheric envelope consistent with potential habitability. The precision achieved in these measurements was extraordinary by any standard. The water vapor detection reached signal-to-noise ratios exceeding 5 sigma, the gold standard for scientific significance. The carbon dioxide detection, while weaker, still achieved statistical significance levels that left little doubt about its reality. Even the tentative dimethyl sulfide detection reached significance levels that, while not definitive, were compelling enough to warrant serious consideration. The data processing pipeline that produced these results represented a tour de force of observational astronomy. Raw telescope measurements were carefully calibrated to remove systematic effects. Stellar variability was modeled and subtracted, and atmospheric transmission spectra were extracted using techniques that pushed the limits of data analysis capabilities. The final spectra emerged from thousands of individual measurements, each requiring precise calibration and careful error analysis. The impact of this data extended far beyond K218b itself. The observations demonstrated that JWST could successfully characterize the atmospheres of potentially habitable sub-Neptune worlds, a capability that opens entirely new avenues for the search for life beyond Earth. The techniques developed for K218b are now being applied to dozens of other potentially habitable worlds, creating a systematic survey of atmospheric diversity on exoplanets. The data that changed everything also transformed the field of astrobiology from a largely theoretical discipline to an observational science. For the first time, we have direct chemical evidence of conditions that could potentially support life on a world beyond our solar system. While we cannot yet definitively state that K218b harbors life, we can now analyze its atmosphere with sufficient precision to search for the chemical signatures that life might produce. This transformation sets the stage for understanding how we might definitively identify biosignatures in exoplanet atmospheres, and what finding such signatures would mean for our understanding of life in the universe. The search for life beyond Earth faces a fundamental challenge. How do you recognize life on a world you've never visited, around a star unlike our Sun, where evolution might have taken completely different paths? The answer lies in understanding biosignatures, the chemical fingerprints that life inevitably leaves in planetary atmospheres, signatures so distinctive that they can be detected across interstellar distances through the subtle filtering of starlight. On Earth, life has fundamentally transformed our planet's atmosphere over billions of years. The oxygen we breathe, the ozone that protects us from harmful radiation, even the precise mixture of gases that maintains our climate, all are products of biological processes. Our atmosphere is essentially a byproduct of life, carrying chemical messages about the biological processes occurring on our planet's surface that could be detected by alien astronomers studying our world from afar. The concept of atmospheric biosignatures rests on a crucial insight. Life requires energy, and the process of extracting energy from the environment inevitably produces waste products that accumulate in planetary atmospheres. These biological waste products often exist in combinations that are thermodynamically unstable. They shouldn't coexist in substantial concentrations unless something is continuously producing them, but something is life. The classic example is Earth's oxygen-methane atmosphere. From a purely chemical perspective, oxygen and methane should react rapidly to produce carbon dioxide and water, eliminating both gases from the atmosphere within a few million years. The fact that both exist simultaneously in our atmosphere is compelling evidence for active biological processes. Photosynthesis, producing oxygen, and methanogenic bacteria, producing methane, remove life, and this atmospheric combination would disappear geologically quickly. For Ca-218b, the biosignature hunt focuses on detecting similar chemical disequilibria in a completely different atmospheric environment. The planet's hydrogen-rich atmosphere creates conditions where different types of biosignatures might be possible, or where familiar biosignatures might be produced through unfamiliar biological pathways. The potential detection of dimethyl sulfide in Ca-218b's atmosphere represents exactly this type of biosignature hunting. On Earth, DMS is produced primarily by marine phytoplankton and certain bacteria as they metabolize organic sulfur compounds. The molecule serves various biological functions. It can act as a signaling compound, help regulate cellular osmotic pressure, and play roles in sulfur metabolism pathways. Crucially, we know of no significant non-biological processes that produce DMS in substantial quantities under conditions like those on Ca-218b. But biosignature science extends far beyond single molecule detections. The most convincing evidence for life would be the simultaneous detection of multiple gases that collectively indicate active biological processes. On Ca-218b, this might involve detecting DMS alongside other sulfur-bearing compounds, organic molecules that could indicate biological metabolism, or gas ratios that suggest active cycling of biologically important elements. The hydrogen-rich environment of Ca-218b opens possibilities for entirely different types of biosignatures than those we see on Earth. In reducing atmospheres, life might produce methane, hydrogen sulfide, phosphine, or other reduced compounds as metabolic byproducts. These molecules could accumulate to detectable levels if biological processes produce them faster than atmospheric chemistry can destroy them. One intriguing possibility involves what astronomers call anti-biosignatures, the absence of certain molecules that should be present in lifeless atmospheres. On Ca-218b, the lack of certain expected chemical products could indicate that biological processes are consuming them faster than geological processes can produce them. This detective work requires understanding not just what life produces, but what it consumes. The temporal aspect of biosignature detection adds another layer of complexity. Life on Earth has changed our atmosphere's composition over geological time, and we might expect similar changes on other worlds. Seasonal variations, long-term trends, or even day-night differences in atmospheric composition could all provide evidence for biological processes. JWST's ability to monitor Ca-218b's atmosphere over multiple transits opens the possibility of detecting such temporal biosignatures. The challenges in biosignature interpretation are immense. Every potential biosignature must be carefully evaluated against possible non-biological explanations. Volcanic activity, atmospheric chemistry, interactions between the planet's surface and atmosphere, or even processes we haven't yet discovered, could potentially produce molecules that mimic biological signatures. The scientific standard for claiming a biosignature detection is necessarily very high. The evidence must be so compelling that non-biological explanations become implausible. For Ca-218b, the biosignature hunt is complicated by our limited understanding of atmospheric chemistry on hydrogen-rich worlds. The reducing environment, different pressure and temperature conditions, and the influence of the red dwarf star all create chemical conditions that don't exist anywhere in our solar system. Theoretical models suggest various ways that biosignatures might be produced, modified, or destroyed in such environments. But these models remain largely untested. The search for biosignatures also raises profound philosophical questions about the nature of life itself. Our definitions of biosignatures are necessarily based on Earth life, carbon-based organisms that use liquid water as a solvent and leave specific types of chemical fingerprints. But life on Ca-218b, if it exists, might operate through completely different biochemical pathways, producing biosignatures we haven't thought to look for. Despite these challenges, The biosignature hunt represents humanity's best current strategy for detecting life beyond Earth. The chemical analysis of exoplanet atmospheres provides a way to search for life that doesn't require traveling to other star systems or waiting for extraterrestrial signals. It transforms the question, are we alone, from philosophy to observational science. The potential biosignatures in K2-18b's atmosphere may represent our first glimpse of alien life, but confirming their biological origin will require understanding the complex chemistry of alien worlds. Part 7. B. The phosphine controversy. 750 words. The detection of potential biosignatures in exoplanet atmospheres carries with it the weight of one of astronomy's most important lessons. Extraordinary claims require extraordinary evidence. The controversy surrounding phosphine in Venus's atmosphere serves as both a cautionary tale and a crucial reference point for evaluating the potential dimethyl sulfide detection on K2-18b. In September 2020, astronomers announced the detection of phosphine in Venus's atmosphere, a discovery that sent shockwaves through the scientific community. Phosphine, a molecule consisting of one phosphorus atom bonded to 3 hydrogen atoms, is produced on Earth primarily by anaerobic bacteria in oxygen-free environments. The detection suggested the tantalizing possibility that life might exist in the acid clouds of Venus, protected from the planet's hellish surface conditions. The initial phosphine detection relied on observations from ground-based telescopes, which detected absorption features at wavelengths characteristic of phosphine molecules. The detection appeared robust, with signal strengths that seemed to rule out instrumental errors or data processing mistakes. Isiderinics Vitesse Cray and Eumidia Bethes phosphine detection relied on observations from ground-based telescopes, which detected absorption features at wavelengths Vitesse phosphine molecules. The detection appeared robust, with signal strengths Vitesse phosphine molecules. The discovery team carefully considered non-biological explanations for phosphine production, but concluded that known geological and atmospheric processes on Venus couldn't account for the observed concentrations. However, the phosphine detection quickly became controversial as other research teams attempted to reproduce the results. Reanalysis of the same data using different calibration techniques yielded conflicting results, with some analyses confirming the detection and others finding no evidence for phosphine. Additional observations with different telescopes produced similarly mixed results, with some supporting the detection and others contradicting it. The controversy deepened as atmospheric chemists developed new models for phosphine destruction in Venus's atmosphere. These models suggested that even if phosphine were being produced by unknown processes, it would be destroyed so rapidly by atmospheric chemistry that detectable concentrations couldn't persist. The hostile environment of Venus's atmosphere, with its sulfuric acid clouds and complex chemistry, creates conditions where phosphine molecules would be broken apart within minutes or hours of formation. The phosphine controversy has continued for years, with different research teams reaching different conclusions about the reality of the detection. Some studies claim to confirm the presence of phosphine, while others argue that the spectroscopic features attributed to phosphine could be explained by other atmospheric constituents or instrumental effects. The debate has highlighted the enormous challenges involved in detecting trace gases in planetary atmospheres and the importance of independent confirmation of potential biosignature discoveries. The lessons from the phosphine controversy are directly relevant to evaluating the potential dimethyl sulfide detection on K2-18b, like phosphine on Venus. DMS on K2-18b would represent a potential biosignature detected at the very limits of instrumental sensitivity. The spectroscopic features that might indicate DMS in K2-18b's atmosphere are weak and could potentially be explained by other atmospheric components or systematic errors in data processing. However, there are important differences between the Venus phosphine and K2-18b DMS detections. The K2-18b observations were made with the James Webb Space Telescope, which offers superior sensitivity and spectroscopic precision compared to ground-based telescopes. The data processing techniques used for JWST observations have been extensively validated through observations of solar system objects and other exoplanets, providing greater confidence in the reliability of the results. The atmospheric environment of KAURS 218b also differs significantly from Venus. While Venus's atmosphere is highly oxidizing and chemically reactive, KAURS 218b's hydrogen-rich atmosphere is reducing and might be more conducive to preserving trace molecules like DMS. The lower temperatures and different pressure conditions on KAURS 218b could allow DMS to persist for much longer periods than phosphine could survive in Venus's atmosphere. The K218b research team has approached the potential DMS detection with appropriate scientific caution, acknowledging that the feature remains at the edge of statistical significance and requires confirmation through additional observations. This cautious approach reflects the lessons learned from the phosphine controversy and the recognition that biosignature claims must meet extremely high evidentiary standards. The phosphine controversy also highlights the importance of theoretical atmospheric modeling in interpreting potential biosignature detections. Understanding how molecules are produced, transported, and destroyed in planetary atmospheres is crucial for determining whether detected gases could be of biological origin. For K218b, this requires developing new models of atmospheric chemistry in hydrogen-rich environments, conditions that don't exist anywhere in our solar system. The ongoing phosphine debate demonstrates that confirming biosignature detections requires not just initial observations, but sustained observational campaigns, independent analysis by multiple research teams, and careful theoretical modeling of atmospheric processes. The potential DMS detection on K218b represents the beginning of this process, not its conclusion. Despite the controversies and challenges, the search for biosignatures in exoplanet atmospheres represents our best current method for detecting life beyond Earth. The lessons learned from cases like the phosphine controversy help refine our approaches and ensure that when we do finally confirm the detection of extraterrestrial life, the evidence will be unassailable. For centuries, our search for life beyond Earth has been constrained by a fundamental assumption that life elsewhere would resemble life as we know it. We've looked for planets like Earth, orbiting stars like our Sun, with atmospheres that mirror our own. But K218b is forcing us to abandon these Earth-centric assumptions and imagine forms of life that could exist under conditions completely unlike anything in our experience. The traditional approach to astrobiology has been guided by what scientists call the Earth template, the idea that life requires liquid water, carbon-based chemistry, and environmental conditions broadly similar to those found on our planet. This approach made sense when we had only one example of life to study, but the discovery of potentially habitable sub-Neptune worlds like K218b is expanding our conception of what habitable actually means. K218b challenges every aspect of the Earth template, which is hydrogen-rich atmosphere, creates a reducing environment, the opposite of Earth's oxygen-rich, oxidizing conditions. Its atmospheric pressure is likely several times higher than Earth's. Its host star emits most of its energy in the near-infrared spectrum rather than visible light. Any life on this world would need to adapt to conditions that would be instantly lethal to virtually all Earth organisms. Yet these alien conditions might not just permit life, they might actually favor it. The hydrogen-rich atmosphere of K218b could provide abundant chemical energy for organisms that metabolize hydrogen, a process that occurs in some Earth bacteria, but is limited by the scarcity of hydrogen in our oxidizing atmosphere. On K218b, hydrogen metabolizing organisms might form the base of entire ecosystems, converting the abundant atmospheric hydrogen into chemical energy that could support complex food webs. The potential global ocean of K218b opens even more exotic possibilities for life. Unlike Earth's oceans, which are exposed to space and vulnerable to atmospheric loss, K218b's ocean would be protected by a thick atmospheric blanket. This protection could allow for the accumulation of complex organic molecules that would be destroyed by ultraviolet radiation in more exposed environments. The ocean might become a vast chemical laboratory where prebiotic chemistry could operate on planetary scales. The depth of K218b's hypothesized ocean, potentially hundreds or thousands of kilometers deep, creates opportunities for vertical stratification of life, unlike anything on Earth. Different depth zones could harbor completely different forms of life, adapted to different pressure, temperature, and chemical conditions. Near the surface, organisms might utilize the filtered starlight that penetrates the hydrogen atmosphere. In the middle depths, chemosynthetic organisms might thrive on chemical energy from atmospheric oceanic interactions. In the deepest regions, life might be supported by hydrothermal activity from the planet's interior. The near-infrared spectrum of K218's stellar output suggests that any photosynthetic life on K218b would need to evolve completely different biochemical pathways than Earth plants. Instead of the familiar green chlorophyll that harvests visible light, K218b organisms might utilize pigments that appear black or deep red to human eyes, maximizing absorption of the infrared-rich starlight. Such organisms might achieve much higher efficiency in energy capture than Earth's photosynthesis, potentially supporting more productive ecosystems despite the dimmer stellar illumination. The chemical composition of K218b's atmosphere also opens possibilities for entirely different metabolic pathways. The abundance of hydrogen and water vapor, combined with trace amounts of carbon dioxide and potentially other molecules, could support forms of chemosynthesis that don't exist on Earth. Organisms might metabolize atmospheric hydrogen to reduce carbon dioxide into organic compounds, creating a planetary-scale carbon cycle driven by biological rather than geological processes. The potential detection of dimethyl sulfide in K218b's atmosphere hints at sulfur-based biochemistry that could be fundamental to life on this world. On Earth, sulfur plays important but secondary roles in most biological processes. On K218b, sulfur compounds might serve as primary energy sources, signaling molecules or structural components of alien biochemistry. The reducing atmosphere could favor sulfur chemistry that is impossible under Earth's oxidizing conditions. Perhaps most remarkably, life on K218b might be inherently more resilient than Earth life. The thick atmospheric protection, stable stellar energy source, and vast oceanic habitat could create conditions where life is less vulnerable to extinction events. Unlike Earth, where asteroid impacts, volcanic eruptions, or climate changes can cause mass extinctions, K218b's global ocean and protective atmosphere might buffer against such catastrophes. Life on such a world could potentially evolve continuously for billions of years without the disruptions that have punctuated Earth's biological history. The possibility of life on K218b also raises profound questions about the prevalence of life in the universe. If life can exist on hydrogen atmosphere ocean worlds, then the number of potentially habitable planets in our galaxy increases dramatically. Sub-Neptunes are the most common type of exoplanet, and many orbit in the habitable zones of red dwarf stars. If even a small fraction of these worlds harbor life, then biology might be far more common in the universe than we've ever imagined. The search for life on K218b is also teaching us about the limitations of our current biosignature detection methods. The molecules we're searching for, water vapor, carbon dioxide, dimethyl sulfide, are based on our understanding of Earth biochemistry. But life on K218b might produce entirely different chemical signatures that we haven't thought to look for. We might be seeing only the tip of the iceberg of K218b's potential biological activity. This expansion of our conception of habitability has implications that extend far beyond a single exoplanet. It suggests that life might be a more robust and adaptable phenomenon than we've previously assumed. Instead of being confined to narrow ranges of conditions similar to Earth, life might be capable of thriving under a wide variety of environmental conditions, using diverse energy sources and chemical pathways that we're only beginning to understand. The study of K218b is transforming astrobiology from a field focused on finding Earth's twin to one that embraces the possibility of life in forms we've never imagined. As we continue to study this remarkable world and others like it, we may discover that the universe is not just capable of supporting life, but that it may be teeming with forms of biology that challenge our deepest assumptions about the nature of life itself. But K218b doesn't exist in isolation. It's part of a complex planetary system with secrets that may reveal even more about the potential for life in alien environments. In the gravitational architecture of the K218 system, there's a mystery hiding in plain sight. The careful analysis of K218b's orbital timing reveals subtle variations, tiny deviations from the clockwork precision we'd expect if this world were dancing alone around its red dwarf star. These transit timing variations, measured in mere minutes across years of observation, whisper of hidden companions, unseen planets whose gravitational influences are detectable only through their subtle tugs on K218b's orbit. The missing planet problem in the K218 system begins with precision. When astronomers predict the exact moment K218b should begin its transit across its star's face, based on previous observations, reality doesn't always match prediction. Sometimes the transit begins a few minutes early, sometimes it's a few minutes late. These variations are tiny, often less than the length of a coffee break, but in the precision world of exoplanet science, they're as clear as fingerprints at a crime scene. Transit timing variations occur because planets don't orbit in perfect isolation. Every world in a planetary system experiences gravitational forces not just from its host star, but from every other planet in the system. When planets orbit close to each other, or when their orbital periods are related by simple mathematical ratios, these gravitational interactions can become strong enough to measurably alter orbital timing. The pattern of timing variations observed for K218b suggests the gravitational influence of at least one additional planet in the system. The most likely candidate is a world orbiting farther from the star than K218b, with an orbital period roughly twice as long. This hypothetical planet, tentatively designated K218d, would complete one orbit for every 2 orbits of K218b, creating a 2-orbital resonance. Orbital resonances are among the most beautiful and stable configurations in celestial mechanics, like musical harmony, where notes with simple frequency ratios create pleasing chords. Planets in orbital resonance create stable gravitational relationships that can persist for billions of years. The Galilean moons of Jupiter, Io, Europa, and Ganymede, are locked in similar resonances, with Ganymede completing one orbit for every 2 of Europa, and Europa completing one orbit for every 2 of Io. If K218d exists, it would likely be another sub-Neptune world, similar in size and composition to K218b, but receiving less stellar energy due to its greater distance from the star. This outer world would orbit at roughly twice K218b's distance, placing it at the outer edge of the habitable zone, or possibly beyond it into what astronomers call the extended habitable zone, regions where greenhouse effects or internal heating could potentially maintain liquid water. The mass and orbital characteristics of the hypothetical K218d can be inferred from the magnitude and pattern of timing variations it induces on K218b. Preliminary estimates suggest a world roughly 1.5 to 2 times K218b's mass, orbiting with a period of 60-90 Earth days. Such a planet would be substantial enough to significantly influence K218b's orbit, while remaining dynamically stable over astronomical timescales. The missing planet problem extends beyond just K218dd. The gravitational dynamics of the K218 system are complex enough that additional smaller planets could exist without being detected by current observations. Rocky super-Earth worlds, small sub-Neptunes that don't transit as seen from Earth, or planets in highly inclined orbits, could all be hiding in the system's gravitational architecture. The search for missing planets in the K218 system employs multiple detection strategies beyond transit timing variations. Radial velocity measurements, which detect the subtle motion of the host star caused by orbiting planets, could potentially reveal additional worlds. Direct imaging, while extremely challenging for planets around red dwarf stars, might eventually detect large, distant planets in the system. Astrometry, precise measurement of stellar position, could detect the gravitational influence of massive planets through their effects on the star's motion through space. The existence of additional planets in the K218 system has profound implications for understanding the formation and evolution of this remarkable planetary architecture. Multi-planet systems provide insights into the disk conditions and formation processes that created these worlds. The orbital resonances and gravitational relationships between planets reveal the migration history that shaped the current system configuration. If K218d exists and orbits in the extended habitable zone, it could represent another potentially interesting world for astrobiology. While likely too cold for surface liquid water, it might harbor subsurface oceans maintained by tidal heating or radioactive decay. The gravitational interaction with K218b could provide the energy necessary to maintain liquid water beneath an icy surface, similar to how Jupiter's gravity maintains the subsurface ocean on Europa. The missing planet problem also highlights the challenges of exoplanet detection. Despite decades of planet hunting and thousands of discovered worlds, we're still finding new planets in systems we thought we understood completely. The K218 system likely contains additional worlds that remain hidden from our current detection methods, waiting to be revealed by more sensitive instruments or longer observation campaigns. Perhaps most intriguingly, the missing planets in the K218 system might be connected by gravitational resonances that create a stable, long-lasting orbital architecture. Such resonant chains are known to exist in other exoplanetary systems and represent some of the most stable planetary configurations possible. The K218 system might be an example of how planetary migration and gravitational interactions can create architectures that maximize long-term stability and potentially enhance habitability. The hunt for K218's missing planets continues, with each new observation potentially revealing additional worlds in this fascinating system. But the planets we can see are already teaching us about the intricate gravitational dance that shapes planetary systems across the galaxy. To hunt for K218, the K218 planetary system operates like a cosmic clock, with its worlds locked in gravitational relationships, so precise that their orbital periods are related by simple mathematical ratios. This celestial synchronization, known as orbital resonance, transforms what could be chaotic gravitational interactions into stable, long-lasting orbital architectures that can persist for billions of years. The confirmed planets K218b and K218c are locked in a 3 orbital resonance, meaning that for every 3 orbits, K218c completes around the red dwarf star. K218b completes exactly 1 orbit. This relationship isn't coincidental. It's the result of a complex migration process that unfolded over millions of years as these worlds formed and settled into their current positions. Orbital resonances occur when the gravitational forces between orbiting bodies create regular periodic interactions that either stabilize or destabilize their orbits. In the case of stabilizing resonances like those in the K218 system, the gravitational interactions act like a cosmic flywheel, maintaining precise orbital timing relationships, even when external forces might otherwise disrupt the system. The 3 resonance between K218b and K218c creates a fascinating pattern of gravitational interaction. At regular intervals, determined by their orbital periods, the 2 planets align in their orbits and experience stronger gravitational forces from each other. These periodic alignments could have dramatic effects on the planet's atmospheres, potentially driving tidal heating, atmospheric mixing, and even exchange of material between worlds. The physics of orbital resonance relies on energy conservation and angular momentum transfer between orbiting bodies. When planets are locked in resonance, energy and angular momentum can be exchanged between their orbits through gravitational interactions, creating a self-regulating system that maintains orbital stability. If one planet's orbit is perturbed by external forces, the resonant relationship acts to restore the original orbital configuration. For K218b, the resonant relationship with K218c provides crucial orbital stability that may be essential for long-term habitability. Without this stabilizing influence, K218b's orbit might be more eccentric or unstable, causing dramatic climate variations that could render the planet uninhabitable. The resonance acts as a gravitational anchor, keeping K218b in the stable, nearly circular orbit necessary to maintain consistent conditions in the habitable zone. The hypothetical third planet, K218d, if it exists, would likely be incorporated into this resonant architecture. The most probable orbital configuration would place K218d in a 2 resonance with K218b, creating a resonant chain where all three planets are gravitationally linked in a stable orbital pattern. Such resonant chains are known to exist in other exoplanetary systems and represent some of the most stable planetary configurations possible. The formation of orbital resonances in the K218 system provides clues about the early history of these worlds. Resonances typically form during planetary migration, when planets change their orbital distances due to interactions with the protoplanetary disk or gravitational interactions with other planets. The presence of multiple resonances suggests that the K218 planets underwent significant migration from their formation locations to their current orbits. The migration process that created the K218 resonance system likely occurred during the first few million years after planetary formation, when the protoplanetary disk still contains substantial gas that could influence planetary orbits. As planets migrated inward due to disk interactions, they became trapped in resonant relationships when their migration rates synchronized with the natural periods of gravitational interaction. The cosmic clockwork of the K218 system also affects the planet's physical and atmospheric evolution. Tidal heating caused by resonant gravitational interactions could provide internal energy sources that maintain geological activity and potentially contribute to atmospheric processes. The regular patterns of gravitational forcing could drive atmospheric circulation, seasonal variations, and even long-term climate cycles. For K218b's potential habitability, the resonant architecture provides both stability and complexity. The stable orbital relationships ensure that the planet remains within the habitable zone over geological timescales, but the periodic gravitational interactions could drive atmospheric and oceanic dynamics that enhance habitability through improved heat distribution and chemical mixing. The study of orbital resonances in exoplanetary systems like K218 is revealing that such configurations are far more common than once thought. Many multi-planet systems show evidence of resonant relationships, suggesting that planetary migration and resonant capture are fundamental processes in planetary system formation. The cosmic clockwork of the K218 system represents a remarkable example of how gravitational forces can create order from chaos, transforming potentially unstable planetary orbits into precisely synchronized celestial mechanisms that operate with clockwork precision across cosmic time. This gravitational choreography may be one of the key factors that makes K218b's remarkable habitability possible. But understanding how these worlds achieved their current orbital configuration requires examining the migration processes that shaped the K218 system's architecture. The current architecture of the K218 system tells a story of cosmic wandering, planets that didn't form where we find them today, but instead migrated across vast distances through their birth system in a process that fundamentally shaped their potential for habitability. Understanding this migration mystery is crucial for comprehending not just how K218b achieved its remarkable 99.7% habitability score, but how planetary systems throughout the galaxy evolve into configurations that can support life. Planetary migration was once considered an exotic process, confined to theoretical models and extreme cases. But the discovery of thousands of exoplanets has revealed that migration is actually the norm rather than the exception in planetary system evolution. Planets commonly end up in orbits far different from where they formed, moved by gravitational interactions with the protoplanetary disk, with other planets, or with the host star itself. The CAR 218 system shows clear evidence of extensive migration. The compact orbital architecture, with multiple sub-Neptune planets orbiting closer to their star than Mercury orbits our Sun, couldn't have formed in place. The high temperatures and low solid material density in the inner regions of protoplanetary disks make it nearly impossible for such massive planets to accumulate directly in their current orbits. Instead, K218b and its companions likely formed much farther from their star, in the cold outer regions of the protoplanetary disk, where water ice and other volatile materials could condense into solid particles. In these distant nurseries, planetary cores could grow large enough to gravitationally capture substantial atmospheric envelopes of hydrogen and helium from the surrounding disk. The migration process that brought these worlds to their current positions occurred through interaction with the protoplanetary disk itself. As young planets orbit within a disk of gas and dust, they create gravitational perturbations that form spiral density waves, regions of slightly higher or lower material density that propagate through the disk. These waves carry angular momentum, and the exchange of angular momentum between the planet and the disk causes the planet's orbit to evolve. For planets less massive than Jupiter, this disk migration typically causes inward migration. The planet gradually spirals toward its host star as it loses angular momentum to the surrounding disk. The migration rate depends on the planet's mass, the disk's properties, and the local disk conditions, but typical migration timescales range from hundreds of thousands to a few million years. The K218 system's orbital resonances, Honborus, provide crucial evidence for the migration process. When multiple planets migrate inward through a disk, they can become trapped in resonant relationships when their migration rates synchronize. The three resonance between K218b and K218c, and the possible 2 resonance with the hypothetical K218d, suggest that these worlds migrated together as a resonant convoy, maintaining their gravitational relationships even as they journeyed across their birth system. This resonant migration process explains how K218b ended up in the perfect position within the habitable zone. Rather than forming in the habitable zone, where conditions wouldn't have favored the accumulation of a massive atmosphere, K218b formed in the cold outer system, where it could acquire its hydrogen-rich envelope, then migrated inward until it reached its current Goldilocks orbit. Afenza if you within gears of Aston War, the Seth T as a 4. The timing of migration was crucial for K218b's current habitability. The planet needed to complete its migration and achieve its current orbit before the protoplanetary disk dissipated, typically within the first 5 mighty 10 million years of system formation. If migration had continued for too long, K218b might have spiraled into its star and been destroyed. If migration had stopped too early, the planet might never have reached the habitable zone. The migration process also affected the atmospheric evolution of these worlds. During migration, planets experience changing stellar radiation environments, different disk conditions, and varying gravitational interactions with other migrating planets. These changing conditions could have driven atmospheric loss, compositional changes, and the establishment of the atmospheric properties we observe today. For K218b, the migration history might explain some puzzling aspects of its atmospheric composition. The moderate atmospheric envelope, thick enough for habitability, but not so thick as to create crushing surface pressures, could be the result of atmospheric loss during migration, followed by stabilization once the planet reached its current orbit. The presence of water vapor might reflect the planet's formation in the outer system, where water ice was abundant, combined with later atmospheric evolution during migration. The migration mystery also has implications for understanding the prevalence of habitable worlds around red dwarf stars. If migration is necessary to place sub-Neptune planets in habitable zone orbits, then the efficiency of this migration process determines how many potentially habitable worlds exist around red dwarfs. Systems where migration proceeds smoothly and planets become trapped in stable resonant configurations might be more likely to host habitable worlds, Recent computational models of planetary migration in red dwarf systems suggest that the process might be particularly efficient around these low-mass stars. The smaller stellar masses and different disk properties around red dwarfs could favor migration processes that place planets in habitable zone orbits while preserving their atmospheric envelopes. The migration mystery of the K218 system represents a remarkable example of how dynamic processes during planetary system formation can create the precise conditions necessary for habitability. The gravitational choreography that moved these worlds from their birth orbits to their current positions may have been essential for creating one of the most potentially habitable worlds we've ever discovered. Understanding this migration story helps us appreciate that K218b's habitability isn't just a product of its current properties, but the result of a complex evolutionary journey that played out over millions of years in the early history of its planetary system. This journey may have been essential for creating the conditions that earned K218b its remarkable place in the search for life beyond Earth. The ultimate test of any potentially habitable world is how it compares to the one planet we know supports life, Earth. When we place K218b alongside our homeworld, the comparison reveals both striking similarities and fundamental differences that challenge our understanding of what makes a planet suitable for life. This cosmic comparison isn't just an academic exercise, it's a crucial step in determining whether K218b could truly harbor the biology that would make it one of the most important discoveries in human history. The most obvious difference between Earth and K218b lies in their sheer physical scale. Whole Earth is a terrestrial world with a radius of 6,371 kilometers and a mass that serves as our standard unit for planetary comparison. K218b is a giant by comparison, with 2.6 times Earth's radius and 8.6 times its mass. If you could somehow stand on K218b's surface, assuming it has a solid surface, you would experience gravitational forces roughly 2.3 times stronger than Earth's gravity. A person who weighs 70 kilograms on Earth would weigh about 161 kilograms on K218b, making even simple movements significantly more challenging. This size difference fundamentally alters the planet's internal structure and dynamics. Earth consists primarily of rock and metal, with a thin veneer of water covering about 71% of the surface. Our planet's average density of 5.5 grams per cubic centimeter reflects this rocky composition. K218b, with its much lower average density of approximately 2.3 grams per cubic centimeter, must contain a significant fraction of lighter materials, most likely water and atmospheric gases. While Earth's oceans average less than 4 kilometers deep, K218b's global ocean could be hundreds or thousands of kilometers deep, containing more water than has ever existed on Earth throughout its entire history. The atmospheric comparison reveals perhaps the most dramatic differences between these worlds. Earth's atmosphere is thin, with a surface pressure of just 1 bar, and consists primarily of nitrogen, 78%, and oxygen, 21%, with trace amounts of other gases. This oxygen-rich environment is actually toxic to many forms of life, and exists only because photosynthetic organisms have spent billions of years pumping oxygen into the atmosphere. Further, K218b's atmosphere is likely several times thicker than Earth's, and consists primarily of hydrogen with substantial water vapor and traces of other molecules. Instead of Earth's oxidizing environment, K218b presents a reducing atmosphere that might be more similar to Earth's early atmosphere before oxygen became abundant. The energy environments of these worlds are fundamentally different. Earth receives abundant energy from our Sun, a G-type star that produces most of its energy in visible wavelengths. This solar energy drives our weather systems, ocean currents, and through photosynthesis, most of our planet's biological productivity. K218b orbits a red dwarf star that produces only about 2.3% of our Sun's luminosity and emits most of its energy in near-infrared wavelengths. Despite receiving much less stellar energy per unit area than Earth, Ke 218b's thick hydrogen atmosphere could trap heat so efficiently that surface temperatures remain within the range where liquid water can exist. The orbital and rotational characteristics of these planets also differ significantly. Earth orbits at an average distance of 150 million kilometers from the Sun, completing one orbit every 365.25 days, while rotating once every 24 hours. This combination creates the familiar day-night cycle and seasonal variations that have shaped terrestrial life. K218b orbits much closer to its star, at about 21 million kilometers, completing an orbit every 33 Earth days. At this close distance, the planet might be tidally locked, with one side permanently facing the star and the other in eternal darkness, though its thick atmosphere could redistribute heat efficiently enough to prevent extreme temperature variations. The geological activity on these worlds likely differs dramatically. Earth's plate tectonics, driven by internal heat and convection, continuously recycles crustal materials and plays crucial roles in regulating atmospheric composition and climate. The larger mass and different internal structure of K218b would create different geological processes. The intense pressure at the bottom of its hypothesized deep ocean could maintain liquid water even at temperatures that would vaporize water under Earth-like conditions. The interaction between this global ocean and the planet's rocky interior could drive unique geological processes that have no parallels on Earth. The magnetic field environments present another point of comparison. Earth's magnetic field, generated by convection in our liquid iron core, provides crucial protection against harmful solar radiation and helps retain our atmosphere. Kia 218b's larger size and different internal structure might generate an even stronger magnetic field, providing superior protection against the flares and particle radiation produced by its red dwarf star. Alternatively, if its internal structure doesn't favor dynamo processes, Kia 218b might rely entirely on its thick atmosphere for radiation protection. The habitability implications of these differences are profound. Earth's habitability relies on a complex interplay of factors: the right distance from the Sun, a protective atmosphere, abundant liquid water, geological activity that regulates climate, and a magnetic field that shields against harmful radiation. K218b achieves potentially similar habitability through completely different mechanisms: a thick atmosphere that maintains temperature through greenhouse warming, protection from radiation through atmospheric absorption rather than magnetic deflection, and a stable global ocean that could buffer against climate variations. Perhaps most remarkably, K218b might actually be more stable and long-lived than Earth's habitability. Our planet's complex climate system, driven by interactions between atmosphere, oceans, ice sheets, and geological processes, can undergo dramatic changes that affect habitability. Ice ages, supervolcanic eruptions, asteroid impacts, and the gradual evolution of our Sun's energy output all pose challenges to Earth's long-term habitability. K218b's simpler system, a global ocean beneath a stable atmosphere, orbiting a star that will remain virtually unchanged for trillions of years, might provide more consistent conditions for life over cosmic timescales. The comparison between Earth and K218b reveals that habitability might be achievable through multiple pathways, not just the specific combination of conditions found on our homeworld. While Earth represents one solution to the challenge of maintaining liquid water and chemical complexity over geological time, K218b might represent an entirely different but equally valid solution. If confirmed, this would suggest that habitable worlds might be far more common and diverse in the universe than we ever imagined, expanding the possibilities for life beyond the narrow Earth-like template that has guided our search for habitable exoplanets. Venus stands as astronomy's greatest cautionary tale about planetary evolution, a world that might once have been habitable but transformed into a hellish greenhouse, where surface temperatures exceed 460 degrees Celsius and atmospheric pressures reach 92 times that of Earth. As we evaluate K218b's potential habitability, The story of Venus provides crucial warnings about how planetary atmospheres can evolve in directions that eliminate any possibility of life as we know it. The Venus warning begins with a sobering realization. Venus and Earth formed from similar materials in the same solar system, yet their evolutionary paths diverged so dramatically that Venus became the most hostile planet in our solar neighborhood, while Earth became a haven for life. This divergence demonstrates how sensitive planetary habitability can be to initial conditions and evolutionary processes that unfold over geological time. Venus likely began with substantial amounts of water, possibly including early oceans that might have persisted for billions of years. But the planet's proximity to the Sun, about 30% closer than Earth's orbit, meant it received significantly more solar energy. As the Sun gradually increased its luminosity over geological time, Venus experienced a runaway greenhouse effect, where increasing temperatures caused more water to evaporate into the atmosphere, creating more greenhouse warming, which caused even more evaporation in a catastrophic feedback loop. The end result was complete atmospheric transformation. All of Venus's water was lost to space, leaving behind a dense carbon dioxide atmosphere with sulfuric acid clouds and surface conditions where lead would melt. The planet's surface is hot enough to destroy organic molecules within seconds, and the atmospheric pressure is so intense that it would crush any Earth-based life instantly. Venus demonstrates how greenhouse effects that start as beneficial climate regulation can spiral into planetary sterilization. For K218b, the Venus warning raises critical questions about atmospheric stability and evolution. K218b's hydrogen-rich atmosphere creates greenhouse warming that maintains temperate conditions despite the planet's orbit around a dim red dwarf star. But could this greenhouse effect become unstable? Could K218b experience its own version of runaway greenhouse warming that would eliminate its habitability? The physics of hydrogen greenhouse effects on K218b are different from the carbon dioxide greenhouse effects that transformed Venus, but the underlying principles remain concerning. If K218b's atmosphere were to become significantly warmer, perhaps due to increasing stellar luminosity, changes in atmospheric composition, or loss of atmospheric mass, the increased temperatures could drive more water vapor into the atmosphere. Water vapor is itself a greenhouse gas, so increased atmospheric water could cause further warming in a feedback process, similar to what occurred on Venus. However, K218b has several advantages over Venus that might protect it from runaway greenhouse effects. The planet's massive atmosphere provides enormous thermal inertia. It would require tremendous energy input to significantly change the temperature of such a massive gas envelope. The hydrogen-dominated composition also creates different greenhouse physics than the carbon dioxide atmosphere that doomed Venus. Hydrogen greenhouse effects might be more stable and less prone to runaway feedback than carbon dioxide systems. K218b's orbital environment also differs significantly from Venus's situation. Red dwarf stars like K218 increase their luminosity very gradually over time, unlike Sun-like stars that undergo more significant brightness evolution. K218 will remain at nearly constant luminosity for trillions of years, eliminating the external forcing that drove Venus's atmospheric evolution. This stellar stability could prevent the gradual heating that initiated Venus's transformation. The depth of K218b's hypothesized global ocean provides another buffer against Venus-like evolution. While Venus lost its water relatively quickly once atmospheric temperatures became high enough, K218b's vast ocean would represent a much larger water reservoir. Even significant atmospheric heating might not be sufficient to evaporate an ocean that could be thousands of kilometers deep. This massive water reservoir could act as a thermal buffer that stabilizes the planet's climate against perturbations. The Venus warning also extends to atmospheric loss processes beyond greenhouse effects. Venus lost its water primarily through hydrogen escape to space, after water molecules were broken apart by solar ultraviolet radiation in the upper atmosphere. K218b orbits a red dwarf star that produces less ultraviolet radiation than the Sun. potentially reducing the rate of hydrogen escape and water loss. The planet's stronger gravitational field would also make it more difficult for atmospheric gases to escape to space. However, red dwarf stars present their own challenges for atmospheric stability. Young red dwarfs can produce powerful flares that blast planets with high-energy radiation, potentially driving atmospheric loss through different mechanisms than those that affected Venus. K2-18b's thick atmosphere might provide protection against such events, but the long-term cumulative effects of stellar flares over billions of years remain uncertain. The Venus warning also highlights the importance of geological processes in maintaining habitable conditions. Earth's plate tectonics helps regulate atmospheric composition by recycling carbon dioxide between the atmosphere and interior. Venus lacks active plate tectonics, which may have contributed to its inability to regulate greenhouse gas concentrations. If K2-18b lacks Earth-like geological processes, it might be more vulnerable to atmospheric instabilities than planets with active geological cycling. Despite these concerns, the Venus warning doesn't necessarily doom K2-18b's habitability prospects. The fundamental differences between these worlds, K2-18b's massive atmosphere, stable stellar environment, vast water reserves, and different greenhouse physics, could protect it from Venus-like atmospheric evolution. Understanding these differences is crucial for assessing whether K2-18b represents a stably habitable world or a planet that might be vulnerable to atmospheric catastrophes over geological time. The Venus warning serves as a crucial reminder that habitability is not a permanent planetary characteristic, but an evolving state that depends on complex interactions between atmospheric, geological, and stellar processes operating over billions of years. The ultimate test of any potentially habitable world lies not in its present conditions, but in its ability to maintain those conditions over the vast timescales required for complex life to evolve and flourish. As we peer into the far future of K2-18b, 1 billion years from now, we encounter a remarkable tale of stability in an evolving cosmos. A world whose fundamental characteristics might remain virtually unchanged long after Earth has become uninhabitable. 1 billion years from now, Earth will face existential challenges that will likely end its status as a habitable world. Our Sun, following the inexorable path of stellar evolution, will have increased its luminosity by approximately 10%, creating a runaway greenhouse effect that will boil away Earth's oceans and leave our planet as barren as Venus is today. The complex biosphere that has flourished on Earth for billions of years will be extinct, leaving behind only geological traces of the life that once transformed our planet's atmosphere and surface. But K2-18b will still be orbiting a star that remains virtually unchanged from today. Red dwarf stars like K2-18 evolve so slowly that 1 billion years represents barely a noticeable fraction of their lifetime. The star will continue producing roughly the same amount of energy, maintaining the same spectral characteristics, and providing the same stable energy input that makes K2-18b's habitability possible. Where Earth will face catastrophic change, K2-18b will experience cosmic constancy. The planet's massive atmosphere will remain its greatest asset in maintaining long-term habitability. Unlike Earth's thin atmospheric envelope, which is vulnerable to various loss mechanisms and compositional changes, K2-18b's substantial hydrogen-rich atmosphere provides enormous stability. The sheer mass of this atmospheric reservoir makes it resistant to gradual erosion processes that might alter thinner planetary atmospheres over geological time. The global ocean that potentially covers K2-18b will likely persist far into the future or protected by the planet's thick atmospheric blanket. This vast water reservoir, containing perhaps hundreds of times more water than all of Earth's oceans combined, provides a stability buffer against climate variations that might otherwise affect habitability. Even if atmospheric processes change the ocean's temperature or chemical composition, the sheer volume of water ensures that liquid water will remain available for any life that might inhabit this world. The gravitational architecture of the K2-18 system will continue to provide orbital stability for K2-18b. The resonant relationships that currently maintain stable, nearly circular orbits for the system's planets are self-reinforcing and can persist for timescales that exceed the age of the universe. Unlike Earth, which experiences gradual orbital changes due to tidal interactions with the Moon and solar evolution, K218b's orbit will remain within the habitable zone indefinitely. 1 billion years from now, if life exists on K218b, it will have had unprecedented time to evolve and diversify. Where Earth's biosphere has had roughly 4 billion years to develop, from simple chemicals to complex organisms, life on K218b will have had 5 billion years or more of continuous stable conditions. 2. The possibilities for biological evolution over such extended timescales are difficult to imagine, potentially producing forms of life and intelligence that bear no resemblance to anything that has ever existed on Earth. The chemical evolution of K218b's ocean and atmosphere over billion-year timescales could create environmental conditions that become increasingly favorable to life. Gradual processing of atmospheric and oceanic chemistry by biological and geological processes might optimize the planet's composition for supporting complex ecosystems. Unlike Earth, where external forcings like solar evolution and asteroid impacts periodically disrupt biological evolution, K218b might experience continuous, uninterrupted biological development. The radiation environment around K218b will also remain benign over billion-year timescales. As the red dwarf star K218 continues to age, it will become even quieter and more stable, reducing any flaring activity that might currently pose challenges for surface life. The planet's thick atmosphere will continue providing protection against cosmic radiation, creating an increasingly sheltered environment for biological processes. Perhaps most remarkably, a billion years from now represents only a tiny fraction of K218b's potential habitability timeline. While Earth's habitable period will have ended, K218b could continue supporting life for hundreds of billions, or even trillions of years into the future. This world might host biological evolution for periods that exceed the entire history of complex life in the universe. Up to this point, the long-term future of K218b suggests that if life exists on this world, it might represent one of the most successful biological experiments in cosmic history. Life evolving continuously under stable conditions for timescales that challenge our ability to comprehend. Understanding this temporal perspective is crucial for appreciating why sub-Neptune worlds around red dwarf stars might represent the future of life in our universe. The revolution in exoplanet science that brought us K218b's remarkable atmospheric analysis is just the beginning. As we stand at the threshold of a new era in astronomical observation, a suite of next-generation telescopes and missions is preparing to push our understanding of potentially habitable worlds to unprecedented depths. These technological marvels will transform our ability to study worlds like K218b, potentially providing the definitive evidence needed to confirm whether we are truly alone in the universe. The James Webb Space Telescope, despite its revolutionary capabilities in studying K218b, represents only the first wave of next-generation astronomical instruments. Currently under development are telescopes with even greater sensitivity, larger apertures, and more sophisticated instruments designed specifically for the characterization of potentially habitable exoplanets. These observatories will build upon JWST's pioneering work, pushing atmospheric analysis to new levels of precision and expanding our survey of potentially habitable worlds. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will bring unprecedented capabilities for wide-field exoplanet surveys. While not primarily designed for atmospheric analysis, Roman's advanced coronagraph instrument will demonstrate direct imaging techniques that could eventually allow us to photograph planets like K218b directly, rather than inferring their properties through transit observations. This direct imaging capability represents a crucial step toward comprehensive characterization of exoplanet atmospheres and surfaces. Ground-based astronomy is also undergoing a revolutionary transformation. The extremely large telescope ELT, currently under construction in Chile, will feature a primary mirror 39 meters in diameter, 6 times larger than the James Webb Space Telescope. This enormous light-gathering power, combined with advanced adaptive optics systems that correct for atmospheric turbulence, will provide unprecedented sensitivity for detecting and analyzing the atmospheres of potentially habitable exoplanets. The ELT will be capable of directly detecting atmospheric constituents in worlds like K2-18b and could potentially identify biosignatures with far greater confidence than current instruments. The 30-meter telescope and Giant Magellan Telescope represent additional ground-based observatories that will contribute to this new era of exoplanet characterization. These instruments will work in concert with space-based telescopes, providing complementary observational capabilities and enabling comprehensive studies of planetary atmospheres across multiple wavelength ranges. The combination of space-based and ground-based observations will provide a level of atmospheric analysis detail that was unimaginable just a decade ago. Perhaps most exciting are the dedicated exoplanet mission concepts currently in development. The Habitable Worlds Observatory, a flagship mission being studied by NASA, would be specifically designed to directly image Earth-like exoplanets and analyze their atmospheres for signs of life. While focused primarily on terrestrial planets around Sun-like stars, such missions could also provide unprecedented insights into sub-Neptune worlds like K2-18b, potentially resolving questions about their atmospheric composition and habitability that current observations cannot answer. So, the European Space Agency's Plato mission will complement these direct imaging capabilities with ultra-precise photometry that could detect even smaller atmospheric signals than those currently achievable. Plato's ability to simultaneously monitor thousands of stars for years at a time will provide the long-term observations necessary to detect seasonal variations, weather patterns, and temporal changes in exoplanet atmospheres. For worlds like K2-18b, such long-term monitoring could reveal dynamic atmospheric processes that provide additional evidence for or against habitability. Technological advances in detector sensitivity and spectroscopic precision will also dramatically enhance our ability to study potentially habitable worlds. New infrared detector technologies will push sensitivity limits beyond current capabilities, potentially allowing detection of trace gases in exoplanet atmospheres at concentrations far below what is currently possible. Advanced spectrograph designs will provide higher spectral resolution, enabling more precise identification of atmospheric molecules and better understanding of atmospheric conditions. The integration of artificial intelligence and machine learning into astronomical data analysis is revolutionizing how we extract information from complex observations. These computational techniques can identify subtle patterns in spectroscopic data that might be missed by traditional analysis methods, potentially revealing atmospheric features that indicate biological processes. For worlds like K2-18b, AI-assisted analysis could help distinguish genuine biosignature detections from instrumental artifacts or atmospheric phenomena that mimic biological signatures. The next generation of exoplanet exploration will also benefit from advances in theoretical modeling and atmospheric simulation. Improved climate models for hydrogen-rich atmospheres will provide better predictions of what biosignatures might look like on worlds like K2-18b, guiding observational searches and improving our ability to interpret detected atmospheric features. Three-dimensional atmospheric models will help us understand how atmospheric dynamics, weather patterns, and chemical processes interact to create the atmospheric conditions we observe. International collaboration is becoming increasingly important in this new era of exoplanet science. The complexity and cost of next-generation telescopes require cooperation between space agencies and research institutions around the world. The coordinated use of multiple telescopes and instruments will provide comprehensive characterization of potentially habitable worlds that no single observatory could achieve alone. The time frame for these next-generation capabilities spans the next 2 decades, with major facilities coming online throughout the 2020s and 2030s. This timeline means that within the next 20 years, we may have definitive answers about the habitability of worlds like K218b and potentially direct evidence for life beyond our solar system. The technological capabilities being developed today will determine whether the next generation of astronomers can finally answer one of humanity's most profound questions. Are we alone in the universe? Imagine being able to take an actual photograph of K218b, not just inferring its atmospheric composition from the slight dimming of starlight during transits, but directly capturing photons that have bounced off the planet's atmosphere and traveled 124 light-years through space to reach our telescopes. This is the extraordinary challenge of direct exoplanet imaging, a technological frontier that represents the holy grail of exoplanet science and our ultimate goal for studying potentially habitable worlds. The direct imaging challenge begins with understanding just how difficult it is to photograph a planet orbiting another star. If K218b were orbiting our Sun at its actual distance, the planet would appear roughly 10 billion times fainter than the star, equivalent to trying to spot a firefly buzzing around a lighthouse from thousands of miles away. But the challenge extends beyond just brightness. Differences. The planet orbits so close to its star that separating their light requires angular resolution capabilities that push the absolute limits of what's physically possible with telescope technology. Current direct imaging efforts have succeeded only with young, massive planets orbiting at large distances from bright stars, worlds that are still glowing with heat from their formation and orbit, far enough from their stars to be resolved as separate objects. These early successes, while groundbreaking, represent the easiest targets for direct imaging. Planets like K218b's, smaller, cooler, and orbiting close to dim stars, require technological capabilities that are orders of magnitude more challenging to achieve. The key to direct imaging lies in coronagraphy, the art and science of blocking starlight to reveal much fainter objects nearby. Solar coronagraphs have been used for decades to block the sun's bright disk and study the much fainter corona. But exoplanet coronagraphy requires suppressing starlight by factors of billions, while preserving the incredibly faint light from orbiting planets. This level of contrast suppression must be achieved while maintaining precise optical stability and correcting for atmospheric turbulence and instrumental imperfections. Several coronagraph technologies are being developed to meet this challenge. Vortex coronagraphs use specially designed optical elements to create destructive interference that cancels starlight while preserving light from nearby objects. Starshade missions would deploy enormous flower-shaped screens in space, positioned thousands of kilometers away from telescopes, to block starlight directly. Internal coronagraphs, integrated into next-generation space telescopes, will use combinations of deformable mirrors, sophisticated optics, and real-time control systems to achieve the stability needed for exoplanet detection. The benefits of direct imaging extend far beyond just detecting exoplanets. Once we can directly observe light from exoplanet atmospheres, we gain access to entirely new types of information about these worlds. Direct spectroscopy of exoplanet light could reveal atmospheric composition with precision impossible through transit observations. We could potentially detect seasonal variations, weather patterns, surface features, and even day-night temperature differences that provide insights into atmospheric dynamics and habitability. For K218b specifically, direct imaging would answer fundamental questions about the planet's nature that transit observations cannot resolve. We could determine whether the planet actually has a solid surface beneath its atmosphere, measure the precise composition and pressure of its atmospheric envelope, and potentially detect gases present in concentrations too low to be detected through transit spectroscopy. Direct imaging might even reveal whether K218b has moons, which could play important roles in the planet's habitability through tidal heating and gravitational stabilization. The timeline for achieving direct imaging of worlds like K218b spans the next several decades. Near-term missions like the Nancy Grace Roman Space Telescope will demonstrate coronagraph technologies on easier targets, paving the way for more ambitious future missions. The proposed Habitable Worlds Observatory could potentially achieve direct imaging of some sub-Neptune worlds, though K218b's distance and orbital characteristics make it a challenging target even for advanced future telescopes. Ground-based observatories, equipped with advanced adaptive optics and coronagraph systems, may also contribute to the direct imaging challenge. The combination of extremely large apertures and sophisticated atmospheric correction systems could potentially resolve planets around the nearest red dwarf stars, though K218's distance of 124 light-years places it beyond the reach of foreseeable ground-based direct imaging capabilities. The direct imaging challenge represents more than just a technological hurdle. It's a pathway to transformative discoveries about exoplanets and potentially life beyond Earth. Success in directly imaging and characterizing planets like K218b would provide the detailed information needed to definitively assess habitability and search for biosignatures with unprecedented sensitivity. This capability would mark the transition from inferring exoplanet properties to directly observing alien worlds, fundamentally changing our relationship with planets beyond our solar system. The moment when humanity definitively confirms the existence of life beyond Earth will represent the most significant discovery in our species' history, a revelation that will fundamentally transform our understanding of our place in the universe and our perception of life itself. For K218b, that moment of confirmation would require evidence so compelling, so unambiguous, that it leaves no reasonable doubt about the biological origin of the phenomena we observe. Understanding what such confirmation would look like and how it would reshape civilization helps us appreciate the profound stakes of our current observations of this remarkable world. Definitive confirmation of life on K218b would likely require the simultaneous detection of multiple biosignature gases in concentrations and combinations that cannot be explained by any known non-biological processes. The tentative detection of dimethyl sulfide that has made K218b famous represents just the first hint of what such confirmation might look like. True confirmation would require detecting DMS alongside other biological indicators, perhaps phosphine, methanethiol, or complex organic compounds, in ratios that clearly indicate active biological production and consumption. The statistical standards for claiming life detection would be extraordinary. While typical astronomical discoveries require significance levels of 5 sigma, meaning there's less than a 1 in 3 whole 5 million chance the result is due to random chance, biosignature confirmation would likely require even higher statistical thresholds. Multiple independent observations by different telescopes, analysis by different research teams, and replication of results over multiple observing seasons would all be necessary before the scientific community would accept a claim of extraterrestrial life. The confirmation process would unfold over years, not months. Initial detections would be followed by intensive follow-up observations designed to test alternative explanations and search for additional confirming evidence. Atmospheric modelers would work to understand whether any non-biological processes could produce the observed chemical signatures. Laboratory experiments would investigate whether the detected molecules could form through purely chemical processes under K218b's atmospheric conditions. The scientific scrutiny would be intense and unforgiving, as it should be for such a momentous claim. Temporal variations in biosignature gases would provide crucial additional evidence for biological origin. Life processes on Earth produce seasonal variations in atmospheric composition as biological activity changes with environmental conditions. This signature temporal variations in biosignature temperature tis signature 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 petit vent de pubit dal fro gendus. Similar seasonal or shorter-term variations in K218b's atmospheric composition, perhaps correlated with the planet's 33-day orbital period, or longer-term climatic cycles, would strengthen the case for biological activity. Weather patterns, day-night variations, or gradual long-term trends in atmospheric composition could all provide evidence for active biological processes. The discovery of life on K218b would be particularly significant because it would represent a form of biology completely different from terrestrial life. The hydrogen-rich atmosphere, different stellar radiation environment, and sub-Neptune planetary characteristics would require life forms adapted to conditions that don't exist anywhere on Earth. This discovery would demonstrate that life is not confined to Earth-like environments, but can adapt to a much broader range of planetary conditions than previously imagined. The implications of confirmed life on K218b would ripple through every aspect of human knowledge and culture. In biology, the discovery would provide the second example of life in the universe, allowing scientists to begin understanding which characteristics of life are universal and which are specific to Earth's particular evolutionary history. The study of K218b's hypothetical biosphere could reveal entirely new forms of biochemistry, potentially based on different chemical pathways or energy sources than terrestrial life. The discovery would transform astrobiology from a field that studies the potential for life to one that studies actual examples of life beyond Earth. Research priorities would shift from searching for potentially habitable environments to understanding how life operates under different planetary conditions. The number of potentially habitable worlds in our galaxy would be reassessed upward, as the confirmation that sub-Neptunes can support life would expand our definition of habitability to include billions of additional worlds. Space exploration priorities would be revolutionized by confirmed life on K218b. While the planet's distance of 124 light-years places it far beyond the reach of current or foreseeable interstellar missions, the discovery would likely accelerate development of advanced propulsion technologies and interstellar probe concepts. The knowledge that a potentially rich biosphere exists on K218b would make it one of the most important scientific targets in the galaxy, driving technological development that could eventually enable detailed study of this alien world. The philosophical and cultural implications would be equally profound. The confirmation that life exists on a world so different from Earth would challenge anthropocentric views of life and our special place in the universe. Religions, philosophies, and worldviews would need to grapple with the reality that life is not unique to Earth, and that biological processes operate throughout the cosmos, on worlds vastly different from our own. The discovery would also raise new questions that could drive scientific inquiry for centuries. How complex is life on K218b? Did it evolve independently from Earth life, or could there be some connection through panspermia or other mechanisms? What can K218b's biosphere tell us about the prevalence and diversity of life throughout the galaxy? Could there be forms of intelligence on K218b? And if so, how might they differ from terrestrial intelligence? The timeline for definitive confirmation of life on K218b depends on technological developments currently underway. The James Webb Space Telescope's observations have provided the first hints of potential biosignatures, but confirmation will likely require next-generation instruments with greater sensitivity and spectroscopic precision. The Extremely Large Telescope, Habitable Worlds Observatory, and other advanced observatories, scheduled for the next 2 decades, could provide the observational capabilities necessary for definitive biosignature confirmation. The process of confirming life on K218b would also establish protocols and standards for evaluating biosignature detections on other worlds. The lessons learned from studying K218b would inform the search for life throughout the galaxy, potentially leading to the discovery of biological activity on dozens or hundreds of other worlds. It would become the process of K218b, but also establish protocols and standards for evaluating biosignature detections on other worlds. K218b might represent not just the first confirmed example of extraterrestrial life, but the opening of a new chapter in which the universe reveals itself to be teeming with biological activity on worlds we never imagined could support life. When we finally know for sure whether K218b harbors life, humanity will have crossed a threshold from which there is no return. We will know with certainty that we are not alone in the universe, and that knowledge will change everything about how we understand our cosmic context and our future as a species. The 99.7% habitability score that made K218b famous might ultimately be remembered as the first hint of a discovery that transformed human civilization. We began this journey 124 light-years from Earth, drawn by a number that seemed impossible, 99.7%. A habitability score that suggested we might have found something extraordinary, a world where life could exist under conditions completely alien to our experience. What we discovered in the K218 system challenges everything we thought we knew about planets and life. This is not Earth's twin. It's something far stranger and potentially more significant. A sub-Neptune world wrapped in a hydrogen atmosphere, a global ocean beneath alien skies, chemical signatures that hint at biological processes operating in ways we never imagined possible. K218b represents a new category of potentially habitable world, one that expands our definition of where life might exist. If confirmed, this discovery suggests that the universe might be teeming with ocean worlds of a type that simply doesn't exist in our solar system. Worlds where evolution has had billions of years to experiment with forms of life that challenge our Earth-bound assumptions. The red dwarf K218 will continue shining for trillions of years, providing stable energy for timescales that dwarf the entire history of complex life on Earth. If life exists on K218b, it might represent one of the most successful biological experiments in cosmic history, organisms evolving continuously under stable conditions for longer than we can truly comprehend. But perhaps most profound is what K218b reveals about the nature of discovery itself. We detected potential signs of alien life, not by traveling to other worlds, but by analyzing starlight that filtered through an alien atmosphere. Through the elegant physics of spectroscopy and the revolutionary capabilities of space telescopes, we can now chemically analyze worlds we will never visit, searching for the signatures that life inevitably leaves in planetary atmospheres. The story of K218b is still being written. Each new observation brings us closer to answering the ultimate question: are we alone? Whether that answer is yes or no, K218b has already taught us that the universe is far stranger, far more diverse, and far more wondrous than we ever dared imagine. As you contemplate the possibility of alien oceans beneath hydrogen skies, I'm curious, what discovery about K218b surprised you most? Was it the planet's massive size, its alien atmospheric composition, or perhaps the sheer timescales over which this world might support life? Share your thoughts in the comments. I read every single one and love hearing your perspectives on these cosmic mysteries. If this journey to K218b has sparked your curiosity about the universe beyond our solar system, I'm grateful you joined me for this exploration. Consider subscribing if you want to continue discovering the remarkable worlds that await us among the stars. Each new exoplanet we study reveals how creative the universe can be in building homes for life. The cosmos is vast and full of worlds we're only beginning to understand. If you're ready to explore more alien worlds and cosmic mysteries, our playlist awaits with stories of planets where diamonds rain from the sky, worlds with multiple suns, and perhaps other places where life has found ways to thrive under conditions we never thought possible. The universe has so much more to show us.